Okay, good morning. So welcome back again. I was told I have to lecture in a sitting position. I'm not used to that, so we'll do the best we can. So the first thing I wanted to do is take a few minutes just to introduce my background, because again, each of you sitting here are coming from a different background. Some are, in fact, can I get a quick survey? How many of you are mechanical engineers? How many are electrical? Okay, and any other disciplines here, computer science or any other discipline here? Electronics, okay, all right. Okay, so obviously we already have a diverse skill set here. My own background is completely from the mechanical side. That's where I grew up, and that's where I've been making a living. So I'd like to tell you a little bit about what we do. By we, I mean the CALS research group that I work with, which will be up on the screen in a minute. So I'd like to tell you a few words about what the CALS Center does in the realm of electronic packaging, because almost everything I say for the next 5 days is going to come from that body of knowledge. So it's good to understand what's the background where this is coming from. Okay. So if we can switch to, first off, obviously I do want to thank again Anandaroop, the IIT Kharagpur, and the GIN network for this opportunity. I'm looking forward to this. I want to thank the CALS Center, which is the Center for Advanced Lifecycle Engineering. The logo is on the bottom left over there. And that's the center that's been around for about a little more than 35 years, mid-1980s. I joined it at the end of 1980s. And I'll tell you in a minute what it does, so you'll get a feel for what's the body of knowledge of packaging that I'm coming from. I don't know everything about packaging. I know some things about packaging. And it'll give you a feel for which parts I know. Okay. To ease into that, I want to start with this slide, and we'll come back to this slide again in the next session. This is, I just stole this from Yole. Yole makes roadmaps, business roadmaps every year. And this is a couple of years old already. And, but it's a nice pictorial representation of how electronics complexity is growing. In fact, just this morning, I was watching BBC News, and they were talking about haptic hands, where now you can actually sense. The brain is now plugged into the sensors on your gripper, and you can actually, just like a normal human hand, you can actually sense what you're holding, what's the texture, what's the stiffness, are you holding something soft, something cold, something hot? All those sensations are now directly transmitted to the brain through a computer that you carry on your back. The sensor is going to the computer, and the computer is going to electrodes that go into your brain. So we are already almost getting to this phase where we are talking about bionic human systems. Okay, but of course there's a lot of ground we still have to cover. That is just in the lab. You can't just walk into a hospital and have yourself fitted out with a bionic arm yet. This is still in the research realm, but hopefully someday we are going to get there. But in the meantime, there's a lot of other exciting domains that we have to negotiate. Probably the most popular one that everyone's talking about is self-driving cars. For years, we thought that is too complex and high level a task for artificial intelligence. We now know that it's not. It can be done. And of course, implementation is still many, many, many years. Well, it's going to be spread over many years because it's already there on many roads in many countries. But we understand that artificial intelligence can support complex high-level functions like that. Then the question becomes, well, what's the hardware you need? The software part we understand, and that's not the subject of this workshop. What's the hardware you need? And that's also humongously complex. It gets very, very complex, very high functionality. A lot of electronics. For example, in an automobile, by year 2020, at least about 35 to 40% of the cost of the car will just be the electronics. Whereas if you go back to 1960s and 70s, less than 5% of the cost of the car was electronics. Now it's 35 to 40%, or going to be by 2020, it'll be 35 to 40%. So that's how much electronics is getting packed into every platform. Our job is to make sure that the electronics world can keep pace with that demand and survive those environments. So electronics that have to survive in the car, if you think about it, ranges all the way from under the hood, in the wheel wells, brakes, okay, to cabin, so vast diversity of environments, and the electronics has to survive all of that. The packaging has to survive all of that. So that's really what this workshop's topic is about. How do you package electronics for these kinds of complex, diverse environments? All the way from stuff that is implanted into the human brain to stuff that's under the hood of your automobile. Everything has to survive, right? And as it gets more and more complex, the old way of building electronics and packaging no longer works. The old way was more of a serial thing. The electrical engineer would do the electrical design, then they would build prototypes, then they'd go to the packaging guy. The packaging person never spoke to the electrical people, and the electrical people had no idea what the packaging people were going to do with the electronics. Those days are gone. You can no longer afford that. The time cycle that you have from concept to market is way too short. You cannot have that kind of a serial process. Everything has to be concurrent. And not only that, as Dr. Bhattacharya said, the electrical design depends on the packaging design. Not every electrical design is packageable anymore for these complex electronics. So right from the concept design, the mechanical engineer, which is the packaging engineers, and the electronics engineers, everyone has to be at the same table coming up with the concepts, detailed design, everything all at the same time. What are the tools you need to do that, right? So yeah, I'm a mechanical engineer. I can sit at the table with you, the electrical engineer, but what information do you need from me, and what information do I need from you? And then how do I use the information you give me, and how do you use the information I give you? Where are the tools? Meaning the CAD tools have to be able to handle the electronics analysis and the mechanical analysis all at the same time. So you can no longer have an ECAD tool separate from a mechanical CAD, and they have to be able to talk to each other. Right? The other aspect is, it used to be that we would build electronics, we would build some kind of a package, then we'd say, okay, build some prototypes, let's test it and see if it works. If it doesn't work, we'll go fix the design. You don't have time for that anymore. If that's how you're trying to do your business, your customers, your competitors beaten you already. They'll have their product on the market long before you are done with the iterations of testing and fixing, testing and fixing. So it has to be, the test just has to be a verification that you've done the job right. Right at the design stage, you need to have the confidence, I've done it right, this is going to survive, which means your design tools have to be able to mimic the environment, the environmental stresses, and the package's response or the product's response to those stresses. Your design tools have to be able to handle that so that by the time you're done with the design, you already know it'll work with a very high degree of confidence. You still test. We're never going to eliminate testing. The testing is just a verification and a confirmation and a demonstration that yes, the design did the job. Maybe there'll be a 1% or 1 to 5% a miss where, yeah, in the design you missed something and the test suddenly showed you. But it better not be more than 5% of the time. Otherwise, you're going to be out of business very soon. Okay, so again, the body of knowledge we'll discuss back and forth over the next 5 days will be what body of knowledge goes into those kinds of design tools that allow you to make sure that the product's going to survive its life cycle. Okay. So now let me tell you a little bit about CALS. So, what's my authority to sit here and talk to you about all this? Well, where does my experience come from? Comes from the center, as I said, the acronym is Center for Advanced Lifecycle Engineering. It started out in mid-1980s with the NSF funding. It's our equivalent of DST, right? So their job is to fund fundamental and applied research. And this center was a special part of NSF. NSF traditionally has funded just basic research. But back in the early 1980s, NSF made a decision that we also have to do more applied research, otherwise industry is not really benefiting. Because you know how basic research goes. You do the research, you write through papers, a few students get a degree, and you move on. The papers sit on some dusty shelf somewhere or in some dusty hard drive somewhere and no one ever looks at it again. So NSF said, no, for applied research, that's not enough. Our job, the center's job, is to actually demonstrate that industry is using the results that we are coming up with. And not only that, a certain percentage of our funding has to be from industry. So NSF will just give us some seed money. Our job is to go to industry and raise more research funds. And you better believe that industry is not happy with you just writing papers and giving out degrees. They want that too, because they want to hire you at the other end, the students at the other end. But that's not enough. They want to know, at the end of the year, they want to know, where's your business case? What did you do for me this year? Otherwise, we are canceling our sponsorship, right? So every year you have to convince industry that you made a difference to their bottom line. We as academics are not used to doing that, but we have to learn how to do it, okay? And that center has been around continuously for the last 30 years. I'd like to think we probably have figured out some parts of the answer how to do this right. I'm not saying we are perfect, but we are doing it well enough that we have managed to survive for 30 years. We haven't died yet. Current size of the center is about sixes, give or take. It's about $4 to $7 million a year. Some years it's more, some years it's less. And for an academic center, that's a reasonably good size. So those of you who have interacted with research centers in the US will recognize that that's a reasonably good size center. It buys you enough money to hire good students, which, by the way, those of you who are students, it's a little different. The system in the US is that the government doesn't pay for the students. The research sponsors, well, the research advisor has to pay for the students out of their research funds. So if I don't have research funds, I cannot hire students. I can hire only as many students depending on how much research funds I have. So $6 million, that's about 70, our center is about 70 students, graduate students, some undergraduate students, research labs, some amount of faculty salary. That too may be totally unheard of here, but in the US, my employer does not pay all of my salary. They only pay 50% of my salary. The rest of it comes from research funds. So that's, again, no research money. You cannot really free up your time to do research over there. Your employer will not let you do that. Okay. So again, bottom line, why am I saying all that? Just to give you a feel for what's the size of the research enterprise that we're talking about. Okay. So it's about 100 people total. That includes faculty like myself. I'm only one of 9 or 10 faculty members there. There's some part-time faculty members there. So about 9 to 10 faculty members, 70 to 75 graduate students, undergraduate students, full-time technicians, and research scientists for the lab. Most of the scientists are postdoctoral. And then we have visiting interns, visiting scientists all the time. So again, because of our persistent survivability, NSF has been impressed. They've given us some awards. So has the University of Maryland. And that's just an aerial view of my campus. But that's not how it looks right now. Right now, looks a little bit like that. I just checked the weather report this morning. They're expecting some heavy snow. So my wife is a school teacher, so she's looking forward to snow because then the school's shut down over there. Okay. All right. So this is just a list of some of the people we work with on an average year, alphabetically arranged, but the names are not really that important. What I want to highlight is what sector of the electronics industry they come from. And you can see they're extremely diverse, all the way from consumer and mobile products like your handheld phones and other devices that you're carrying around, to all the way to military and medical and aerospace electronics that have to survive very specific, in some cases very harsh environments, and in some cases like medical, very specific, bio-specific environments. And in addition, our sponsors are government labs, government research agencies like NASA, like Navy, Air Force, and so on. Also Department of Commerce, and so on. We work with, I heard names like Intel and GE and GM. We work with all of them. So they're all sponsors. So for example, GE Industrial Systems is a big sponsor. Well, our sponsorship comes from GRC, GE Global Research Center. And in fact, as a matter of fact, I myself spent 10 years ago, about 6 months at the Jack Welch Center in Bangalore as part of my sabbatical. Some of my students used to work here. They've now moved on to GE in Munich. Okay, so that's our research base. Once again, the reason I mentioned that, it gives you an idea of what kinds of environments our electronic have to survive, and therefore, by our, I mean electronics that we help our sponsors do research on. We don't build electronics. We help our sponsors figure out the durability of their electronics. And if you look at which parts of the supply chain we mostly interact with, which parts of industry, we don't, and I know many of you are down at this level. Interestingly, most of our sponsors are up at this level. A few down at this level, almost none at this level, okay? Which means we don't do a lot of work on silicon or any semiconductor reliability. Our work starts really over here at the first level packaging. We do time to time have some issues that our sponsors bring us at this level, but maybe 5% of our research is in that level. Most of our research starts at this level and steadily goes upstream from there on out. And I just picked one product since I was carrying a Microsoft product today. I put that one up. But our sponsor base, as I mentioned, would be from aerospace. So that could be an airplane, that could be an automobile, that could be a human system for bioelectronics, medical electronic systems, or so on. So it's that upper 2/3 of the supply chain that we mostly deal with. What we do, again, just to round out our portfolio, our number one mission still is we are a university. We do a lot of research, but at the end of the day, we're still a university. Our number one product is not knowledge. Our number one product is what's sitting in the back of the room, students. Okay, it's not just knowledge. Students with that knowledge is what industry is here to buy. And so our first and foremost goal is education. So we support, actually our department is somewhat unique in that respect, in the sense that we have a specialty just in electronic systems packaging. That's somewhat unique. Not too many universities have that. So we offer, courses are at the master's level and PhD level all the way up to doctoral. So we have a total of about 12, 15 courses that we offer with students take as they go through the, again, unlike in the European system, and I'm not sure how it is right here, but do PhD students take coursework here or just do research?
They have some courses.
They have some courses. For us, it's pretty intense. All the way until PhD, you take a lot of coursework. And so we have a suite of about 15 courses that we, 15 to 20 courses that we offer to support all the know-how that's being generated in the electronics packaging area. And so our students actually have a specialization, just like you'd specialize with solid mechanics or MEMS or heat transfer. Just like that, we have a specialization just in electronic products and systems. Okay, then obviously managing that research consortium, I mentioned all those companies we work with. So managing those research consortia and doing those shared research projects in that consortium, that's part of our work. Separate from that, we also offer, just since we have extensive facilities, we also just do testing and analysis for industry. So they may not be a member of the consortium, but they may have a small project that they need someone to do a failure analysis, someone to do a design assessment for them. We do those as just separate standalone projects. And then large research contracts, that's every university does that from the various funding agencies like NSF, DOE, DOC, et cetera. And then this is somewhat unique too. This came about because we work extensively with industry. Almost all the faculty members and research scientists in Cal, including myself, we sit on standards boards with, in different societies. Whoever writes standards, IEEE, IPC, SAE, IEC, they all write standards, and we sit on those standards boards along with other industry and research personnel to bring our inputs to the table, so that makes it into all the standards. In fact, CALS has been very instrumental. I'll talk about that maybe on the last day if we have some chance. There are about 5 or 6 reliability standards out of IEEE that were almost exclusively authored and managed by CALS. So the chair of the board over there was the CALS director, Michael Pecht. Okay. So that's somewhat unusual. Usually university faculty don't get involved in standards activities. We do, and we made that decision intentionally with encouragement from NSF so that our body of knowledge makes it into industry practice standards. Okay, so I won't spend time on this slide. This is, I keep talking about the fact that yes, you need a large body of facilities and labs to manage this kind of research. So again, it would be interesting really to see what kinds of labs we have. Obviously materials characterization, because if you talk about electronics have to survive environments, that means electronics should not fail. What fails in electronics other than software? It's materials in the electronics, right? So unless you understand how materials behave, you cannot design robust electronics. So materials characterization is our number one task. So that's the beginning and the ending of our work is with materials characterization. The other big part, Professor Anandaroop will talk much more about that on day 4, is thermal management. Electronics generate a lot of heat. It goes with the territory, and as your electronics get more dense, functionally and physically, morphologically gets more dense, you have to manage all the heat that comes out of it. So we used to have in the old days, just air cooled or just a fan like in your computer, a fan can cool it, to more modern electronics where you have to cool it on chip. So I'm assuming you'll probably talk more about that. Directly on the silicon chip, you're going to have to do your cooling. Otherwise, there's just too much heat building up. We have 3D die stacks. You have to remove all that heat. Okay? So thermal management has become an extremely challenging and extremely sophisticated problem. Servers, the world of servers is a world of thermal management, right? Okay, this is a buzzword. All it means is design for reliability. Okay, virtual qualification is, remember I talked about you have to be able to assure at the design phase that your design is robust. You can't wait to test it, that's too late. So what kinds of tools do you need to do that? So we spend a lot of time developing, putting our physics of failure models into software tools so that they can be integrated into the CAD tools for design purposes. So that's what we mean by virtual qualification. Optomechanics test. So this is kind of a niche test that we have, and that's because one of the faculty members, Professor Bhante Han, who I'll acknowledge later on in my later slides, because a lot of the material I'll present over the 5 days came from him. He's a specialist in optical methods for mechanical measurements. So you may have heard of methods like Moray methods, Moray interferometry and so on, where you can, or DIC, digital image correlation, where you can measure deformations optically, non-contact measurements. And here's the problem. In the world of electronics, we're talking about very tiny, very slender feature sizes. I cannot put sensors on that to measure. I cannot put a strain gauge, an extensometer. I cannot make any mechanical measurements on those. I cannot measure forces, nothing. So you need non-contact measurements with sub-micron resolutions. So optical methods are obvious candidate for that. And Dr. Han is one of the world's leading experts in that. Environmental and accelerated testing, a lot of my own work is done over here. So we still do a lot of environmental testing because the design tools that we are building have to be verified, have to be validated, model constants have to be calibrated. So we do a lot of accelerated stress testing, thermal cycling, power cycling, temperature, humidity, bias, shock, drop, vibration, you name it, we do various kinds of tests. And I'll talk more about that later on. So some of our test labs are geared just towards that. And then obviously sample preparation. When you've got complex products like electronics, how do you do sample preparation for failure analysis? That's not simple. So we spend a lot of time doing that. And non-destructive evaluation, X-rays, and other non-destructive methods. And then I mentioned finally, workforce training is one of our key goals. Education and workforce training is one of our key goals. So we have labs and studios that support just that. Okay, this is what we do. So I'm going to go over this chart once now, and I'll be going over this at least once a day, I think, over the next 5 days. Okay, just to remind you, because this is it. This is the core of everything I'll talk about for the next 5 days. Don't worry about that text right now. Let's just go through this bubble chart, and I'm going to start at 12 o'clock, and I'm going to go counterclockwise through it. Okay, so this is our fundamental body of knowledge that we are trying to generate. That's where our basic research is. That's understanding material behavior, how they react to different kinds of stresses that electronic products see throughout their life cycle, and how they react to it. Mechanical stresses, chemical stresses, meaning harsh chemicals, and then either in the environment or in the manufacturing process itself introduces harsh contaminants. So how the materials react to that. Electrical stresses, thermal stresses, how do electronics react, or high energy particle radiation. We do some of that for sponsors like NASA, SpaceX, and so on. What else? Acoustic environments, how do electronics require, because obviously a lot of electronics nowadays are sensors. You heard Dr. Bhattacharya talk about it. MEMS is now directly integrated into your electronics. So how they're going to react to acoustics, to pressure, all of that. Okay, so that's what I mean by the physics of failure. That's our core DNA. That's all the faculty members that work in our center are at least an expert in this area. In addition, we then learn some aspect of application of this body of knowledge. In my own case, I spend a lot of time extending that body of knowledge through design tools, so our sponsors can use those design tools to make robust designs. And I do a lot of accelerated stress testing. So these first 3 bullets are mostly where my work is. I play a peripheral role here, but there are other faculty who are the central core of what we call the diagnostic and prognostic health management. And that is, you've heard this before, I'm sure, every complex system nowadays, whether it be electronic or not, Complex systems fail, they degrade, they age over time, and they fail. So you need some kind of an age meter now, okay, that can tell you in real time what fraction of the life has been used up, and therefore what fraction of the life is still remaining. That's a very broad statement. I'm going to explain that a little bit. Let's take this. Let's say you and I go out and buy the same computer. You have a different way of using it. I have a different way of using it. Maybe yours, just saying, maybe yours mostly sits in your office and you have a different laptop you take back and forth to work and travel. And maybe this is my travel computer. I'm traveling all over the world with it. Then our usage is very different. Microsoft, but it's the same design. Microsoft didn't design it separately for you and separately for me. They just took all our possible use conditions in consideration and made some kind of a worst case design or average case design. So clearly your computer is not going to last the same amount of time as mine. Mine, I'm probably using its life up more rapidly than you would if it was just sitting in a benign office environment. How do I keep track of it? I mean, Microsoft probably sold it as, oh yeah, that's a 3-year product. Well, yours may go 6 years and mine may only go 2 years because I'm abusing it. Can I keep tabs on what fraction of the life I've already used up with my rough usage? Versus can you keep tabs on how much life yours is used up and how much life is still remaining? Well, it turns out you can get reasonably good ideas with the right sensors, enough number of sensors and the right kind of sensors in there, and knowing what to do with that sensor information, you can make some pretty intelligent guesses of what fraction of the life has been used up and how much is still remaining. So that is becoming almost a given now in most complex systems because the designer simply cannot design complex systems for everybody's need. And the world has the user community in the world is way too diverse, as I just gave an example. People are using products in many different ways, in many different environments. Someone using the same product in Singapore is seeing a different rate of aging than someone sitting in Finland. The environments are entirely different. So real-time health management, health monitoring and health management is therefore one of the key tools that reliability engineers are resorting to nowadays. So this kind of real-time measurement, sensing, and processing that information, and that's not simple. There's the amount of data analytics that's required to take all that sense information and make a useful conclusion out of it is not trivial. So what they do is collect maybe about 100 different signals out of this, including stress sensors that are sensing the temperature and the humidity and the number of shock drops, the number of turn-on, turn-offs, continuously combining that with the performance measurements they're making all over clock speeds, frequencies, temperature of the various chips, etc. And with all that information, they're trying to compare that to what a healthy product would look like, and has the parameters that you're measuring deviated in any significant way from what a healthy population looks like. And that takes when you're talking about a set of measurements with 100 different parameters, trying to compare two populations is a complex task. So you need very sophisticated data analytics to do that. Okay, so the world of data analytics is very, very useful for this task too. Okay, and again, as I said, I am not. I have a peripheral role in that. I don't play the primary role in that. I play almost no role in these last two bullets, the one at 4 o'clock here and 2 o'clock here. Supply chain management, that's again super critical. In the world of electronics, I just showed you the kind of supply chain. This is probably made in one continent. This is probably made in another continent, third, fourth, and fifth. By the time you're in this product, it's very hard to know who, sometimes you don't even know who made this. I mean, if you're in a reputable company, then yes, you know where this came from. But for a lot of consumer electronics, they don't even know where their parts came from, okay, who manufactured it, let alone the details of what materials went into it, what kind of testing did they do, what were the design practices. Like, I don't know, I bought it from a local distributor, it had some stamp on it, I don't even know if the stamp is real, this is what I have. Okay, and I'm talking about that's at the low end. You go out and buy a toy, electronic toy, for a few hundred rupees. You're not going to get any supply chain information with it. On the other hand, if you're Intel, yes, you're keeping close tabs on who you're supplying to. If you're Intel supplying to Dell, Dell knows exactly what you're doing, and you know exactly what Dell is expecting from you, right? But that's only the high end of the supply chain, not the low end of the high end products, not low end products. So trying to keep tabs on the supply chain, at least for high-end products or high-rel products, really high reliability products, is a key task. What does that mean? Well, let's say I'm here and you're here. What information do I need from you in order to make sure that my product is robust, right? So I could tell you, hey, give me a good chip. You're going to say, well, what do you mean by good chip? What do you need from me, right? So how do I give you the right specs based on the right physics of what my product is going to see, what your chip has to survive? And vice versa. If I say, well, Intel, how do I know you've got a reliable chip and or a robust chip and a robust part? You may say, well, here are the materials I'm using, here are the kinds of tests it survives, here are my overall design practices that I can share in the public domain, or if you sign the NDA, I'll tell you more. Is that information going to make any sense to me? I need to be knowledgeable enough to look at that information and make a quantitative decision what it means to my reliability of my product. So what is the language of that conversation? I don't mean is it English or Bengali or Hindi. I mean what body of knowledge has to pass back and forth to very precisely, quantitatively, for me to be able to make decisions about how robust the product is going to be for my use condition. So that is what we mean by physics of failure aspects of supply chain management. And again, that's a highly non-trivial task, and there's an entire group within our center that manages that. And finally, at the end of the day, because we are a center that works primarily with industry sponsorship, and we are required to, that's what our mission is from NSF, at the end of the day, industry says, did you save me any money? If not, sorry, we are withdrawing our membership. And if I say, well, you tell me, you're the one running the business, I have no idea how to put your work into a dollar amount. You tell me. And so increasingly we were facing that challenge that we had to make the business case for industry. So if you are sponsoring research from Intel and CALS has to make a business case to industry at the end of the year. What did we save Intel potentially as a result of this work? That takes, number one, close interaction between whoever our gatekeeper, our point of contact at Intel is going to be for that research project, the corresponding point of contact in CALS, and then some way to put our research contributions into a dollar amount. So that's, again, not trivial at all. It has to do with what is Intel going to do with that information, what product is going to go into, what kind of a life cycle robustness has it helped that product gain, what does that mean to Intel in terms of sales, potentially, because we don't have Intel sales models or anything, but potentially for an average company, what would that mean in terms of sales, in terms of warranty cost? How do you do all those calculations? You can, but that's not my job. I'm not a researcher in that area. If I spent all my time doing that, I wouldn't have time to do the green box, right? So we have a separate group of researchers who just do just that. So their job is to take every reliability task and convert it into a dollar amount. And by the way, that helps not just us make a business case to our sponsors, but our sponsors make a business case within their own administration chain. The reliability team can now tell the administration, the VP of research, hey, reliability just ended up saving the company so many $1 million in warranty costs over the next 5-year period. We need more resources. So these cost models, life cycle cost models I'm talking about, are very generic. Anyone can take these and implement them within their own company. Okay, so, and I think I'll stop this introduction. That tells you pretty much everything we do, and I'm going to now jump into the main sessions. I do want to explain this one word that I've put over there, cradle to cradle. That's a term we like to use a lot. And that has to do with this term life cycle. Here's the problem. If I want to make my design more robust, I need better materials, more analysis, more testing, in order to guarantee I've got a more robust product. Administration says, no, we're cutting costs. You're dreaming. I'm not giving you more money to do all that. I got to cut costs, not spend more money. Now, the problem becomes if that cost is coming only out of the design center's budget. If you then say, that's cool, let's look at the cost across the maintenance group, which is paying out the warranty costs, and the design group, and let's see if we are spending overall more or less. Because you and I both know as engineers, common sense tells us that if you under-design the product, your warranty costs are eventually going to go up. So let's average the cost across both of those. That's what we mean by whole life cycle cost. Not just the design cost, not just the manufacturing cost, but the life cycle cost, including the cost of sustainment of the product throughout its life cycle. And you may still not come out ahead. The administration may still say, you know what, I'd rather pay that warranty because at the end of the day, you asked me for too much money. So that kind of life cycle cost would be what we call cradle to grave approach. Okay? And the slang for that is womb to tomb. I didn't know that term until recently. So the womb to tomb cost is the life cycle cost. And sometimes you may find that, well, to come up with a new generation of products, the cost of development is so high that even if you average over the whole life cycle, the cost of assuring design assurance or reliability assurance is too high. Then you step back and say, all right, that's not the right cost model either. Let's look at the enterprise cost over the next 10 years. That means if I invest this money developing these materials and these design aspects now, can I reuse that in my next generation product and therefore lower the cost of the next generation product, be faster to the market with the next generation product and beat out my competitors? So it's an investment for the next generation product. And that's where the term cradle to cradle comes from. We're not just talking cradle to grave cost of this generation of products, but cradle to the next cradle of the next design, next generation product. You start looking at enterprise cost in that manner, and then it becomes a lot easier to justify to the bean counters, the business people, why they need to spend more money on reliability, and then where to find the optimum points, optimum cost points, price points for the product over the multiple life cycles. That means life cycle of this generation, next generation, and so on. Okay. Anyway, that's where the term comes from, so I just thought I'd explain that. Okay, this is just sales people who are using our softwares. I'm just going to skip over all that, but you recognize some names, of course, GM and so on. Yes, sir?
I have one question regarding the recycling, because
yes,
after producing all the, after it goes to the tomb.
Absolutely, absolutely. So that is very much a part of life cycle cost now, as you know, in a lot of companies. So, for example, if you buy almost any product in Europe, US is still further behind, and I'm saying US mostly because most of my research practice is with companies in the US. But if you look at Europe, they are far more stringent on they go definitely beyond the tomb to how is this product going to be disposed of. Absolutely. And so cost of disposal is now a part of the life cycle cost in a lot of reputable companies.
Much of the Chinese goods don't talk about it, they talk about use and throw.
China has just banned, I'm not answering your question, unfortunately, but just to show you that the mindset is changing, China has just banned dumping of wastes, especially electronic wastes, from all over the world. About 60 to 70% of electronics waste used to go to China. They just banned it about a week back. So the entire world is reeling from that, and the disposal model has to change around the entire world. We are now forced, too late in my opinion, but we are now forced to, well, not too late, should have been earlier, but we are now forced to consider where is all this waste going to go, where's the cost of disposing all that waste going to come from, and how do we figure that into the life cycle cost? Yeah, absolutely, yeah. And by the way, I'm sorry, so the people who are working over here in this group are very much dealing with those cost items now. Yeah. Okay, so I'll skip over that, and I just mentioned that it's not enough for us to just write papers, declare victory, and move on. We have to transfer all of our knowledge into industry, but that doesn't mean we don't have to write papers. Our main boss is still the university. University says no papers, no degree, no promotions, no nothing, right? So at the end of the day, we are still a university, and if you go to our websites, there are literally thousands and thousands of papers over there that you're never going to be able to complete reading. We have very, very productive team over there. The students, the faculty, they are extremely productive. So almost all our information ends up in technical journals first, conferences and technical journals, and then goes out to industry. Okay. Well, sometimes it's the other way around too, because industry sometimes wants those results before you can actually publish it in the public domain. So sometimes it's the other way around. Okay. So let's start with the first session. Any questions, by the way? Let's take a quick breather. Any questions? Again, why did I go through all of this? Just to give you a background for which body of knowledge am I coming from. So everything I tell you is informed by that experience. And there are a lot of things I don't know. I'm not an electrical engineer. I'm not an electronics engineer. The last time I read a book on electronics was probably in my undergrad days, which was not in this IIT, but one of the other IITs, okay, a very long time ago. Of course, I have to brush up on all that as part of my work, but I'm not an expert in electronics. So, I'm a mechanical engineer out and out. So I will still talk a little bit about electronics because that's the anatomy of the systems we're dealing with, but I will talk about it in novice layman terms almost, okay? Okay, and that's why I put up that disclaimer over here. When I say the title says design, I think the title of the workshop says design. Onwards, I snuck that word mechanical in the front and hit it in gray. That's mostly what I'll be talking about. But when I say mechanical, what I really mean is the non-electrical aspect. It's not just mechanical. It has chemical, because there are harsh chemicals in the environment. Products have to survive that. So it's multi-physics, okay? But what we mean is beyond the electrical and beyond the electronics. What else do you need to know to design successful packages? Okay. Sorry, let's get into...
One point for mechanical.
Yes, sir.
We only talk about the stress strain diagram for failure.
Mm-hmm.
But what about plastics? They don't follow at least most of the composites and things like that, we don't know how to take.
Yeah, we're going to talk a little bit about that.
And how that is affected by corrosion. So these two things I think have to be included.
Yeah. So you make an excellent point. There are two aspects to what you said. One is do plastics fall? I mean, can you draw a stress strain diagram for more exotic materials? For example, plastics. Well, yes, you can, but it depends now on a lot of things. It depends on temperature. It depends on the loading rate. It depends on, am I going to just load and hold it over there? It'll continue to deform and creep. It depends on, is there moisture in the environment? Sometimes it even depends on, is there a magnetic field or electrical field that this piece is embedded in? Or other chemical in the environment, all of the surface condition, the stress strain curves can change the so-called stress strain curves can change as a function of all of that. So we'll be talking about some of that. Unfortunately, all we have is a 5-day course here, so I can only briefly touch on some of those aspects. And then you also mentioned composites. Most real materials have microstructures that are very complex. And can you really talk about just a simple stress strain curve for complex systems like that? And what about all the internal non-uniformities of stress fields? Because you may see a global stress that you're applying, average stress that you're applying, but within the microstructure, it's way more complex. And how does that affect failure? We'll be talking about some of that. Yeah, good. But again, I'll only be able to touch on some of those topics. There's no way to really dive in depth into all of that, right? Okay, just for continuity, I put up that same chart that you already saw. So I'm not going to spend time on that. Oops, I'm in the wrong presentation. Sorry. Oh, not that one. This one. Okay. Okay. All right. So, this chart again, I'm just easing my way into the technicalities. This is just to remind you that yes, partly enabled by IoT. Now electronics is literally in everything, and there's definitely a digital convergence. That means more and more systems are now talking to each other. So that's one kind of communication convergence. Then there's convergence in terms of technologies, because in order to do all this, all your electronics, your photonics, your MEMS, your bio sensors, everything now has to start talking to each other. They have to go into common platforms, and they have to survive the same environments. So there's convergence both on the hardware side and on the communication side. There's tremendous convergence going on. And partly the cloud has enabled us to do that. But the point is now we're dealing in a very complex ecosystem, and our electronics have to be able to deal with all of that. And as Professor Dasgupta said in the morning, and Anandaroop said in his opening statement, you can't ignore electronics anymore. Okay, it's now a multi-trillion-dollar industry, bigger than steel, bigger than automotive. It is the king now. Okay, so the world of electronics is going to rule from now on out, and it's only going to get bigger, not going to get smaller, right? So this is it. This is the center stage of the world for the next decade, at least. And I thought that was an interesting piece of tidbit. 3 years ago, our number of mobile devices surpassed the number of people on this planet. Okay, that's how many devices each. We know that not everyone's carrying a mobile device, which means the rest of us are carrying so many around that we have outstripped the number of people who are not carrying any. Right? Okay. Okay. I'm going to skip over this. So this basically saying that we no longer sit and input stuff. The data is automatically being imported from sensors. Simple thing like I no longer type, I talk into my computers, right? My computer knows how to convert that into information it needs. I don't even have to talk. It looks and converts that into information, right? I want to know where that picture is from. I point my iPhone at it. iPhone says, oh yeah, it came from website so-and-so, right? So sensors do all the inputs. I no longer need to take care of all that. So things are talking to each other. Human beings are becoming irrelevant pretty fast, right? Okay. But here's the crux, and this has been said right from the first speech today, this morning. You can't just take your bare silicon, or not even silicon, whatever the new transistors are going to be, gallium arsenide, indium phosphide. We are continuously upgrading our semiconductor materials. But the point is that you're not just going to shove your semiconductors out there and say, go do your job. The packaging is everything. So without the right packaging, they're not going to be able to do their job. So how can you design your systems with the right packaging to do all of these complex functions that we're talking about? Okay, here's just a simple example. This is all of you are carrying one of these. So here's the kind of complexity we're talking about today in a mobile device. Soon it'll get a lot more complex, right? But at least as of today, you've got power supplies, battery, you've got displays, you've got central processors, you've got memories, you've got signal processing, you've got a little bit of sensors, right, already. You know your iPhone has cameras and accelerometers and pressure sensors and moisture sensors, so all of the basic sensors. And that's only going to grow, right? So that's the body of, that's our sandbox. That's where we're going to play, okay? And the point is, I keep mentioning the word multiphysics. It's not just mechanical, it's not just electrical, it's not just thermal, it's chemical, it's acoustic, it's everything, okay? And EMI and high energy particle radiation, all of those are affecting the system. And the other key aspect of this, and this is what makes, and I teach all of us who teach in the electronic products and systems group in Maryland, make it very clear to our students that what we are really dealing with is a tremendous range of scale. We're not just in the world of nano, we're not just in the world of macro, we have to bridge the gap. We need to know how to go from nano, because all our features are down in the nano size, right? If you look at your semiconductors today, what's the feature size of the leading edge of the feature size of semiconductors today?
16 nanometers.
16? 1.6? It's already gone lower than that. Commercially available extensively is 10 nanometers. Intel's been manufacturing it, Samsung's been manufacturing it, right? TSMC has been manufacturing it. And they're now all playing with prototypes already available in 7 nanometers. Though Intel, I think, has already announced that they're not going to do a large-scale commercialization below 10 nanometers with today's technology, with today's semiconductor technology. They're moving away to either other semiconductors, non-silicon-based semiconductors, or they'll be completely different molecular electronics, but that's still way out, not today. But people are looking at getting away from conventional notion of semiconductors and going into molecular electronics and so on.
Is there a physical limit?
Absolutely, absolutely. You are now hitting gate thicknesses of a few molecules.
Right.
It just doesn't work. Now you're in the quantum domain, and your principles of the continuum principles of electricity that you're using, or electronics that you're using, Maxwell's laws just don't work. You're down to quantum physics here, and those phenomena are now the quantum phenomena are starting to interfere with the functionality. Not to mention, we don't even know how to fabricate or process at those length scales anymore, right? Because think about the masks that you're going to make your semiconductors, right? We are already in the far ultraviolet, and we're hitting the diffraction limit where we cannot get much smaller than that. Okay, And from the functionality, I mean, the material just doesn't work as a semiconductor anymore because now you're in the quantum domain. Right? Okay, which is why you need to go to molecular semiconductors now, which are using quantum phenomena for semiconductor effects. Okay. And again, are those possible? Absolutely. Have they been demonstrated? Absolutely. Can you make it on a commercial basis? Not yet. Okay. All right. A lot of people have made single molecule transistors in the lab. Question is, how do you interconnect to those? How do you build 1 billion of those on a chip, or several billions of those on a chip, with high yields? And most important, how do you package them? Meaning, how do you interconnect to those? Right. Okay. So that multi-scale aspect. So you're talking about phenomena that are happening at the nanoscale, below 10 nanometers now, all the way up to micron scale, milliscale, and sometimes even higher, because electronic systems at the end of the day, when I'm dealing with something like, because I'm a human being, I cannot see nanometers, I cannot deal with nanometers. I need something I can hold at the millimeter scale and above, right? So we have to be able to bridge those length scales. Okay, skip over that chart, just to remind you how complex things are getting. And so here's the kinds of chips that we are building these days. Again, this is not new to many of you. We are long past the days of single chip packaging. Each IC now has multiple chips, sometimes side by side, sometimes stacked in 3D. So these are the so-called 2.5 dimensional. That means these are all on a common substrate, whereas here there's no such substrate or interposer. They're all directly die on die on die stacked, and then they have to talk to each other through the thickness direction, which is why you need vias that go through the silicon. TSV, as many of you already know, is through silicon vias, right? So those are interconnections that are made in the thickness direction, so these multiple dies can talk to each other. But coming back to Anandaroop's world, how on earth do you remove all the heat from these things, right? So you cannot try to cool it from outside. They're going to burn each other inside. You need to be able to cool that chip directly on chip, so it's not overheating the chips next to it and so on. So a lot of MEMS technology is being exploited to do on-chip cooling and so on. And then, of course, we'll talk about the rest of the terminology and the taxonomy of what are all these remaining pieces, what are those spheres over there. We'll talk about all of that throughout the rest of this course. I'm not going to spend too much time on it. This is just to tell you that industry is hitting this hard limit, hitting the wall in terms of how many more chips I can put on each semiconductor piece. And therefore, they're saying, well, I cannot put more transistors on a chip. I'm going to give you more chips instead. Right? Of course, more chips is not as fast as putting them on the chip, but we have hit the limit of how many we can put on the chip. So it's either stop expanding or start making multiple chips talk to each other and try to make it in compact stacks so they can talk to them reasonably fast, but still won't be as fast as if they were talking to other transistors on the same chip. So that's what the term, and you already heard Professor Bhattacharya mention more than more. Moore's law used to govern the roadmaps of how many more transistors you could put on the chip. How many of you know Moore's law? How many of you know who Moore is? Okay, a lot of you don't. Gordon Moore, founder of the company that these guys are from, Intel's founder. Okay, so he made a statement, and I'll put it up. I think it's here. Here we go. I think I have it. No, I didn't put it up here. So he made a statement that the number of transistors on a chip will double every 18 months. Yeah, will double every 18 months. That's the rate at which technology was progressing back when he made that statement. And to his credit, or to his vision, credit to his vision, it continued all the way up until a couple of years back. Now it's started to flatten out because we are hitting the hard limit of how much smaller we can make transistors and pack more transistors in the same chip. But Moore's law actually lasted well into 2014, 15 or so.
Like the national debt?
So, say that again?
Like the national
Like the national, it kept getting extended, yeah. So every year they would say, well, we're still on. So if you draw, and I'll show you one of those charts later on, if you draw the doubling every 18-month graph, you'll see that all the leading companies like the Intels and the AMDs and Samsungs and their products actually kept pace with that curve. But now we're starting to flatten out. And now the only way to keep extending functionality is so now if you buy an Intel processor, they'll tell you how many cores it's got, quad core, dual core. Well, now they are putting more cores, multiple chips, and putting chips either side by side or on top of each other to make them talk to each other even faster, 3D die stack. So that's how we are trying to extend the functionality, try to keep up with Moore's curve, not Moore's law, but Moore's curve. Having said that, that's now a challenge for the packaging people. How on earth do you package so many things together and still make it reliable, get all the heat out, make the interconnection so you can talk to all the chips can talk to each other, the outside world can talk to the chip can talk to the outside world. How do you get all those IOs in and out? You're talking thousands and thousands of IOs per chip. You get 15, 20,000 IO chips very easily nowadays. Okay. Okay, and the second part of the complexity, we already mentioned this when I talked about the Internet of Things, is the convergence of different technologies now. And again, Dr. Bhattacharya also mentioned it. It's not just electronics anymore, your MEMS and sensors, all the logic, the memory, the photonics, other bio sensors, all of that has to now be on common platforms, common packages, and be able to survive the same environments, be able to talk to each other, be interconnected to each other, and so on. So packaging is it. Without packaging, none of this happens. So lots of jobs coming up in packaging, people in the back. So this would be a good area to get into, okay? Okay, and this graph is, again, something I just stole. All these graphs, by the way, I didn't make any of these pictures. I just found nice pictures that convey a good message. I stole those to bring it up for discussion here. This, again, is from Yole. It's a very famous consulting group that makes roadmaps, okay, technology roadmaps. And this is their rendition or depiction of, on one axis, they're talking about, well, let's go with this axis. On this axis, they're talking about putting more transistors on a chip, right? Higher density on the chip, that's SoC, okay? Versus on this axis is when I cannot put more chips, more transistors on a chip, I start adding more chips of different kinds, and that is system in package. SIP stands for system in package. This stands for system on chip. So here you're putting more and more functionality on the chip. You're putting more and more chips together to make up a package with more functionality. And again, you can see there's multi-technology here, RF, MEMS, and so on. Okay, power, CMOS, everything combined here. Digital, analog, everything. Okay, so that's what they're talking about as 3D integration.
So are all these blocks getting added as the things become smaller? Or?
No. It's not, it's and. So things are getting smaller, and on top of that, there are many functional requirements that require all of these extra technologies. So if I'm going to build sensors into my electronics.
13 nanometer, you can have more technologies than you have at 14?
Oh, no. I see what you're saying. This is actually the axis. They're putting these technologies on the axis, and they're putting these technologies on this axis.
So with time it's improving.
Yeah. So most of these, so to make the point, most of these are actually probably up here. Yeah. Okay. Yeah, you make a good point. This is not a very well-made chart. It's a little misleading. Okay. Okay, and this is just putting in words, putting in letters what I've been saying in words all the time, that now you have to worry about electrical, thermal, other mechanical considerations like mechanical stresses, and other life cycle considerations. Well, what's missing here is chemical, right? So chemical plays a big role. Harsh chemicals come from the environment. Harsh chemicals come in the product itself as part of the manufacturing chemicals, okay, processing chemicals. So all of those eventually cause aging of the system. So chemistry is key. So again, in the world of packaging, you have to be a master of many fields, or at least a jack of many fields. You need to understand a little bit of all of these because they're all interrelated, okay? And then that's how you ultimately make life cycle decisions or design for the life cycle. How do you design a reliable product? How do you maintain quality through your manufacturing process? How do you do all that in an affordable way? Because at the end of the day, we're engineers. Someone once joked with me about what's the difference between nanoscience and nanotechnology. I was actually part of a research proposal at the university, writing a proposal to NSF on nanotechnology. And my dean said, well, what's the difference between nanoscience and nanotechnology? And I remembered something that I'd heard some other scientists say on a TV interview, and I repeated it back to him. He said, nanoscience costs money. Nanotechnology makes money. So if you can't make money at the end of the day, you're out of business. So affordability is the key thing. you need to be able to make it cheaper than your competitor and cheaper than your selling price, right? Otherwise, you're out of business. So although we say cost, someone else's problem, it's not. Because if you make it someone else's problem, they're going to put a cheaper material in the product you designed, and you're stuck being responsible for poor reliability because the VP of the CTO comes back and tells you, wait a minute, you designed that product and now it's not working. And you can tell them, well, someone else cut the material cost, and he's going to say, or he or she is going to say, and what were you doing while they were changing the material? You didn't evaluate the material? So you need to understand the cost impact of every decision. Okay.
Which is why Coke is as respectable as Nokia.
I missed the analogy. Go ahead.
Coca-Cola does not have any technology, but it makes money. Whereas Nokia has all the technology and it's going.
Right. So that was another interesting blurb I saw somewhere just a few days ago. Think about all the people making money now. Uber doesn't own any cars, right? Amazon doesn't make any products. And I forget the list. There's again, the Alibaba, and there are a list of 7 or 8 companies like that are now the world's leaders, but they don't make any product. They're just middlemen. They are buying from one person, selling to another person, and they're the ones making the money. So as engineers who are not in that business of just buying and selling, well, some of us are sales engineers or purchasing engineers, but some of us are in the task of making things, right? Some of us have to be. Otherwise, if there are no things, no one can buy and sell things if we don't make those things, invent those things. But those are not the ones making the money, interestingly. Some of those companies, in fact, as you said, like Nokia, are going down the tubes if they don't understand the cost impact of their decisions. So it's a complex world. It's a very complex world. Well, if you talk about really making money, it's even cheaper not to do any of those. Just buy and sell stocks, right? The biggest names on Wall Street, the biggest, most richest people on Wall Street don't even sell a product or a service. They just buy and sell stocks, right? They buy and sell money. Okay, so it's really, what business do you want to be in? I guess that's the question. I chose this as mine, so we have to know something about that at least. Okay, so here's, and I put mechanical in quotes because, as I pointed out, it's not all just mechanical. It's well beyond just what we traditionally call mechanical engineering. So, and I mentioned the word material several times. That's at the core. How robust your system is starts with how robust are the materials that you picked. Of course, that's not the end of it, because you could take the most robust material and do a poor design with it and a poor manufacturing with it and end up with a bad product. But it starts with the right material. And how robust? Only as robust as you need. And I think more than that, you're costing a company money. Okay? So how robust do you need? Well, that depends on what the application is and how well do you understand where the limits of the product are to survive that application. You don't want to put in any material that's more expensive than the minimum you need to survive your product. That's the engineer's job. Okay? So not an easy job, unfortunately. Okay. Then comes the next step. As I said, you could take the best material in the world, do poor manufacturing with it, and kill the material. Be so full of defects that it never survived. Especially at the length scales we are talking about in electronics, the material defects is everything. The material dies because of internal defects. All materials have defects, and it's the defect density that'll make your product different from the next person's product. And controlling those defect densities is absolutely key, which is why semiconductor manufacturing, which is at the lowest rung of the chain of electronic products, is so difficult. I mean, think about the number of people, number of companies that are still in the business of having large-scale foundry capabilities. We have shrunk from hundreds of companies around the world, maybe thousands, to tens of companies around the world. It's the investment needed to keep up with today's technology at the foundry level is humongous, billions and billions and billions of dollars. Okay. Size and weight, that has to do with, again, if we are designing products, it's not enough to, and again, I'll give you that example that I mentioned earlier of what I saw this morning on TV of the bionic arm. The first one they built in the lab had electronics in a whole rack, and imagine walking around with a bionic arm with trailing a rack behind you, right? The version that they showed today, that the person was actually walking around with, you still have to wear a backpack with all the electronics in it, the processing electronics in it. But they're hoping that the electronics are going to get to a level where you can wear it almost as a watch, or maybe someday just implant it under your skin. But we are still a ways away from that, okay? But someday we are going to get there. But size and weight, especially in the world of electronics, is key. Whoever makes it smaller, lighter, prettier, wins, okay? Apple and Nokia may make the same product, but if Apple makes it look smarter and has a better sales force, they win, okay? Okay, power and thermal management. I don't need to beat that to death. You understand in electronics, world of electronics, that's absolutely key. This is the rest of the environmental stresses. Shock, by shock I mean dropping, okay? Drop it and it suffers a shock. Vibration, transportation electronics, automobiles, aircraft, rockets, ships. They have to survive very high vibration environments, or even defense electronics, munitions have to survive very harsh vibration environments. Pressure, again, electronic sensors that you make for deep sea applications or high altitude applications have to survive, or industrial applications where processes are going on at high pressure and you have to be able to control that process with sensors inside the pressure chambers. So pressure is key over there. Acoustic loading becomes important in many applications. Power temperature cycling, I already mentioned that earlier. And then chemical environments. I'm sorry, I'm not sure how I missed that over there. That's key. Harsh contaminants in the environment or in your materials that come from the processing are extremely critical. Critical enough that I would say at least 30% of the work we do in the center nowadays has just become chemical. People are coming back to us with failures that are root caused down to the presence of some chemistry or some chemical that either came from the environment or was trapped in the product as a contaminant from the fabrication process, manufacturing process. And that is the body of knowledge that we use finally to ensure that the product is durable, maintainable, and so on. And then I did mention economics and life cycle already. Okay, this is just to give you an idea of how complex things have become. I need to speed things up here. So that's 1960s vintage electronics, mostly through-hole parts, discrete, small transistors, a few transistors per substrate, big TO cans for transistors and so on, okay? Discrete passives. So all the way from there to 1970s when we first start to put multiple chips in hybrid packages. MCM stands for multi-chip modules. Those were mostly, in those days, we weren't sure how well electronics would survive environments. We used to put them in hermetic packages, very expensive, either ceramic or metal cases. We put the electronics in there, seal them hermetically, and then mount them on circuit cards. Those were very expensive. Eventually, we just moved, as you well know, into plastics molded electronics to make things cheaper. So that's through the 70s and 80s. By the way, the slide was made last year, so that's why everything is in sevens, okay? Ends with a 7. And then we start to get more and more miniaturized plastic encapsulated ICs with surface mount parts, surface mount passives. Gone are the days of through-hole parts, okay? We still have some through-hole parts, but mostly surface mount. And then now we're getting to thinner, more flexible electronics. That's already by mid-2000s that started. We're now printing most of those electronics, okay, 3D printing, additive manufacturing as opposed to subtractive manufacturing. So that's where we are now. Electronics are becoming more and more 3D, printed, well, subtractively done when the design allows, but in some designs some 3D designs you cannot make them subtractively. You have to do it with a combination of subtractive and additive manufacturing. So that's where we are headed, and that's the.
In the 60s it was only pocket calculators, or?
Pocket calculators had already started, some high-end desktop ones. Now, not really pocket calculators, were still mostly desktops. But think about spacecrafts, large mainframe computers. Those were very prevalent in those days. I mean, amazingly, somewhere in 2005 timeframe, we actually got involved with some 1960s vintage electronics because NASA came to us with some of their solid rocket boosters that go up with the space shuttle, or used to. Space shuttle's been decommissioned. used to be used for the launch, and then the boosters would be ejected that fall back into the ocean, and the space shuttle used to go off into space. Those boosters would then be dragged back from the sea by barge back to shore and refurbished for the next launch. Those were reusable. And those were meant for 30 missions, 30 launches. So sometime in the mid-2000s, NASA came and said, look, we already put them through 45 missions, each of them, and we want to know whether we can put them through more. Because the shuttle missions did not end till about 2013, 12, 13. So they still wanted 5 more years out of them. So they wanted us to do a life cycle assessment and say how much life is left in these electronics. So that's how I got a chance to see up front some of those electronics, really the details of it, and see what kind of technologies they had used. And they were extremely robust back then. Few ICs, big packages, big lead frames, through-hole, thick solder boards. No wonder they lasted that much beyond their intended life. And actually, the assessment we made said they're good for another 5 years, and they used them for another 5 years, all the way to the end of.
We add any new things to make it work?
We actually did, but interestingly, it was all on the not on the electronic side, but the boxes, the mounts for the boxes had fatigued. You could see fatigue cracks in those. So it's only the externals that we had to change. The electronics we never had to change. Okay. And this just shows you that we were talking about miniaturization. This shows you how the length scale of things are getting smaller and smaller. This is still an old iPhone, as you can see. This is back in 2010. Today's iPhone already looks a little bit different. But the point is, as we miniaturize and put more and more functionality in smaller and smaller spaces, we are running into the end of Moore's law, basically. Okay, so we need smarter packaging. Otherwise, we're not going to be able to do it. So yes.
I have one question.
Yeah, absolutely.
So we are going to these courses, right?
Mhm.
So I have been in a couple of lectures about this packaging
Mhm.
and all the things in different
Mhm.
scenarios. Can you go to the 2 slides back? Just before that. Next one. No.
Forward. I'm sorry. Okay.
Yeah. just-
Okay.
So any lectures, right? Whatever we're discussing about a packaging or any other things, we'll discuss in the point wise, which is the initial thing, and we'll go like a cycle,
Mhm.
and finally it will come to the cost cycle.
Yes. Mhm.
Cost is the main.
Mhm.
But finally it ends up any packaging, whatever we do, R&Ds or whatever we do, manufacturing or anything. Finally it goes and ends in the cost. Why the cost is not in the input, the one,
Yeah.
instead of in the final stage?
No, it's not the final stage. So the
No. So whenever we discuss about anything, right?
yeah.
So finally only will be discuss about a cost.
So that's a
But-
wrong.
but
That's
that
that's a
is-
wrong approach.
But
That's a wrong approach.
Actually, the cost is the main criteria which drives everything.
Yes.
together, right?
So if you look at people who are doing it the right way, they're starting with a cost budget. They're saying this product is going to be marketed, here's the price point for sale. Otherwise, we're not going to be able to compete, right? This is going to be the final cost. This is going to be the functionality. Now you do a cost budget level by level. Therefore, I can put this much money for display, this much money for power supply, this much money for memory, this much money for processing, and so on, and this much money for sensors. That's your budget. Now, sensor group, you go do your job. Power supply group, battery group, you go do your job. But at the end of the day, I need a battery that can deliver so many milliamp hours for a period of 5 years at this cost. It cannot cost more. So cost is, and then they are breaking it down from there, saying, well, which technology should we go with? Do we have to invent a new one now? They are working now with battery manufacturers to do that. So everything is cost-driven in industry. The cost is not the last, it is the first. The starting point is cost, and from there you work downwards to see what technology can you afford with that cost. There are a few exceptions. There are a few disruptive items that comes up with a totally brand new technology that has no competitor, and you better believe they're going to charge you for it. Okay?
Yes, the premium cost.
Yes. They're going to say, it cost me $100, I'm going to charge you $1,000. Because that's going to pay my development cost and it's going to make me money till my competitor comes up with one. The minute my competitor has one, I'll drop that 1,000 to 200, right? But until then, it's an opportunity cost. So cost drives everything, trust me. It's industry is...
I know that because we are, most of them are students.
Sure, sure.
And the class is going on like this, and then they need to know. Because whenever I go to any classes, right,
Sure.
the cost will be in the lab. The students need to understand that what is actually in the industry. The first in the table.
Good point. I appreciate that feedback. Good point. That's for you guys, okay? Right? Okay, let's move on. All right. So I also, sorry, I owe the people who are doing the recording and they actually did mention that don't take too many breaks for questions and answers. Try to save the questions and answers for end, because I think they're trying to make modules that they're going to save for video purposes. So they didn't want too many interruptions in that module. So if you can kindly look into that, whether that's what they intended or I misheard them. Okay, okay, yeah, all right. Okay, so this is a very classical chart. I just took it out of one of the standard handbooks of electronics packaging, and you can see it's a pretty dated one. But it does have all the right terminology, so that's why I'm using it. It basically shows that you make your semiconductors, right, on a wafer. So you you slice these wafers out of long ingots, and you grow the ingots, single crystal ingots. Then you slice them into wafers. You put all the electronics in it. Then you dice them out. You then package that electronic appropriately, right? That's what we call the first level packaging. So everything that's directly on the chip, we call that zeroth level packaging because there are interconnections in there too. From there, putting that chip into this package, we're going to use the word first level packaging. All the interconnections and all the materials used there are for first level. Okay. Then putting those packages on a circuit card, we're going to call that second level. And then everything beyond that, the circuit card in a rack in a box, all of that is third level. Okay, so that's the terminology that's commonly been used in the world of packaging. The interesting thing, of course, is that a lot of modern electronics don't follow rigorously all of those steps. For example, what do you call it when you take a silicon die and directly flip chip bond it on a circuit card? You've entirely skipped the first level. Is that a second level or is that a first level? You've basically skipped one level in between. So there are always exceptions to this hierarchy. But by and large, this is the terminology that's followed. Okay. Okay. And then this is just reminding you of the feature sizes. In this particular case, I'm just showing some ceramic capacitors, multi-layer capacitors. These are some of the larger capacitors in use. And you can see relative length scale. Can't really interpret that as actual size. Think of it as a relative size. So that's how tiny the 0402s are, okay, in millimeters and in inches. Compared to the 2512. So these are just acronyms, or rather catalog numbers for multi-layer ceramic chip capacitors. You can see some of those parts over there. Those are chip capacitors. So against that human finger, you can see how tiny they are. Okay. Okay.
5 centuries.
No. 2512 is just a part number, catalog number. Yeah. Okay. All right. And over here, I've tried to also show you a different visualization of how the complexity and the convergence is happening. So remember, we talked about system on chip being more and more electronics right onto that silicon IC itself. That means directly onto that silicon chip. So putting in more and more functionality on that chip would be system on chip, versus running into a limit of how much you can put there and starting to put more and more chips in each package would be system in package. So that's what you're seeing over here. So those are multi-chip modules. You're putting more and more chips either side by side or on top of each other in 3D die stacks. So those are systems in package. And there's a little bit of subtle differences between system on a package versus system in a package. There are some subtle differences. I'll come back to that later on. But the point of this slide is that the system complexity and the integration is growing radically, and how to package all of that in a way that they can electrically and mechanically function in a robust way is the challenge. Okay? And once again, everything you're doing here, silicon on chip, follows Moore's law. Everything you're doing outside of the chip is what industry calls more than more. Okay, so that's just a buzzword. Okay, this just talks about some of the components that are relatively hard to put directly on the chip, the passives, the power supply, MEMS devices. Well, MEMS actually you can put on a chip, but more and more the MEMS is a separate chip and everything else, the electronics is on a separate chip. The cooling systems that you're going to put, the other sensors and actuators and other higher level interconnects, those are hard to put directly on the chip. So those you need these kinds of solutions to add those, okay, the lower part of the chain here. Okay, let's move on. I'm going to skip over these two because I'll be talking later on about the difference. So these two charts really talk about the difference between SIP and SOP. That means system in package versus system on a package. So here the substrate itself is a very complex conglomeration of packages, whereas here the substrate is relatively simple. Most of the intelligence or the functionalities on the chips that are on the substrate. Whereas here the substrate itself is a high functioning package itself, and you've got more packages on that package. Okay? But again, this gives you an idea of the complexity of the system, and you can see all the different technologies that are going onto it. Your MEMS, your opto, that's a photonics, your RF, everything is going onto the same product here. Okay? Okay, and this gives you an idea of those newer systems are slowly starting to take over. So you can see back in 1985, the dominant technology was system on board, and by system on board we mean this kind of technology, system on a circuit board. Okay, so back in the 80s, that was the dominant form of electronics that we had. So you can see most of the electronics industry was system on board. But now you can see it's down to barely 50%. By 2020, prediction is only half the electronics industry will still be doing those traditional form factors. Most of them are moving into integration, system on chip, system in package, system on package, and so on. Okay, skip over this one. This saying the same thing over and over again with many different pictures, systems in package. They are complex systems, okay? Oh, so we should be winding up soon. Okay, so this is sort of, after everything I've said, this is just a full circle just to remind you that those complex systems are for what you're trying to understand. What are the degradation mechanisms? Think about what are the source possibilities of failures in a complex system like this. You've literally thousands of materials, thousands of potential failure sites, and you have to design each and every part of it to be robust enough for your application. Okay? So it's not a trivial task at all. It's not something you do manually. You need very sophisticated CAD tools to do this in an automated way. So that's where the future is, and that's where we need you guys. My job is almost over. I've been working 30 years plus, and my job is to now put the bug in your ear, so you guys go ahead and do the next part of the job. Okay? All right. And when we say it has to survive environments, we mean all of these kinds of environments. They're either, these catastrophic overstress events or just routine use. So here, for example, is thermal cycling on a daily basis. So this is just a 24-hour thermal cycle that a laptop computer saw. This is actual measurement. We put a sensor on a laptop computer for one of our students and just monitored it through the day while he came from home, worked all day, went out for lunch, sat in a coffee shop, worked, went back home. We just monitored the temperature sensors that whole day, and this is what we saw. Question is, even if I collect it, what am I going to do with it? That's a horribly complicated looking piece of information. How do I convert it into something that a CAD tool can say, okay, with that information I can tell you how many such days this product is going to last, right? How do I extract useful information out of that for the CAD tool? Well, that depends on what inputs does your failure models need or your design models need. For example, many of the failure models we use look at that and say, oh, that's cyclic temperature, that's cyclic expansion and contraction, that's cyclic fatigue loading, right? So what do I need for that? I need to know how many cycles of what magnitude that history has. So that's cycle counting. Look at this figure on the bottom. I know you cannot read the axes from there. On the horizontal axis is the magnitude of that cycle, and on the vertical axis the number of such cycles. So out here are very large amplitude cycles, and there are few of those. Out here are the tiny cycles, and there are many of those. with some distribution in between. But there are algorithms that will do cycle counting on that complicated profile and convert into something like this. And this I can use, input that into my fatigue models, and it tells how many such days can I survive. So extracting information out of data is a big part. That's data analytics. Okay? So we need to talk about how electronics have to survive those kinds of environments, and that's what we'll do for the next 5 days. I think this is a great time to stop. Yeah. Okay, let's take a break. Okay.
We'll take a little break, tea snacks break, and then come back in 15 minutes.
Okay, all right. Okay, so just for continuity, this is where we stopped. And I made the statement that electronics have to survive these various kinds of environments. And I'm intentionally putting two sets of pictures. These are what we will call overstress events throughout the life cycle. And this is what we're going to call wear-out events. That means this is going to happen throughout the life cycle, no matter what. Okay? These you try to minimize, right? We always try to avoid this. This is not avoidable. This is part of the functional capability of the product. It has to be designed to survive this. And these will activate a certain set of degradation mechanisms. These will trigger a different set of degradation mechanisms. So when we talk about physics of failure and coming up with design models, we will talk about wear-out models for these, and we'll talk about overstress models for these. And the designer deals with those separately. Okay? All right. So just keep those two words in your mind, because we'll come back to it. Overstress mechanisms and wear-out mechanisms. So wear-out mechanisms are like cumulative damage. Every day it has to survive this temperature environment, and it has to survive 3 years of that. Okay, so it's a cumulative wear-out damage, hence the term wear-out. And these are overstress events. The failure happens when that event happens. Okay? So the idea is never to let your product get exposed to such a severe overstress event. But if it happens, the product dies right there. Whereas here it has to survive 3 years or 5 years of this environment. Okay. Okay, so now when I say it has to survive and I talk about degradation, I want to give you a few quick examples of what I mean by degradation. That means how does the material react to these stresses? What happens to the material? So if you think about it, and I keep using the word multi-physics, that means there's electrical damage due to electrical stresses, damage due to mechanical stresses, thermal, so on and so forth. So let's look at some simple examples, and we'll go into this in more detail later on. But here's just a quick collection of some examples. So think about all active devices. And by active devices, I mean anything with a semiconductor chip in it. It could be a MEMS. So that, by the way, is a MEMS microphone. This is the MEMS sensor. This is the ASIC next to it. ASIC is application-specific IC. That's for the signal conditioning. Okay. So that's a MEMS microphone. That's probably in your that's in your cell phone. The microphone that picks up your sound looks pretty much like that. And then that's just a regular IC, logic IC. Here is an LED IC. This is an IC that gives out all your LED flashlights and LEDs on your phone and so on. That's an LED IC. So these are all examples of active devices. Anything, thank you. Anything where you're packaging a semiconductor component. And what kinds of failures do we see in those? And you'll see, I'll go through a much more exhaustive list later on, but here's a few examples. We see electromigration failures, and I'll explain what all of these are later on. But basically what happens is when you have a high current density, you actually physically knock out metal ions from the lattice. In this case, that's an aluminum trace on a semiconductor substrate, and the continuous current density has knocked out aluminum ions from the lattice and created that void. Where did those ions go? Well, they actually land up somewhere else and form a hillock, and I'll show you examples of all of that. Okay, so that's one degradation. So years and years of current density going through a product is going to eventually cause failures due to phenomena like those. So the whole idea is that you design your product to be robust enough. That means you design the metallization to be robust enough that it can survive 3 years of this kind of current densities. Okay. Here's another example. These are wire bonds. So I'm going to get out of this mode and zoom into this a little bit. So here's a typical anatomy of a packaged IC. Here's this here's the semiconductor, silicon chip, and that's been molded inside this mold compound. It's on an organic laminate in this case. And you can see that, well, I don't know how well you can see it. I'll zoom in even more. And we're starting to lose resolution here. But this chip has to be connected. All the ICs and the electronics on that chip have to be connected to the substrate so that they can be connected to the next component, the circuit card. And if you look very carefully, and maybe you can see it in your handout, there are wire bonds coming out from that chip and getting connected to these bond pads here. So the bond pads on the chip, bond pads on the substrate, and there's thin, slender wire bonds connecting them. And then you can connect to these bond pads from the other side, from the underside of the laminate, and now you can go have electrical signals going in and out of the chip. So those bond pads also happen to be a source of failures. Why? Two reasons. One, whenever this mold compound heats up, each time you turn on the IC, it heats up, the mold compound expands. That's plastic. Plastic expands a lot. The wire is metal. That's not going to expand. So so now you've got this wire with this plastic under it, which is trying to expand, and it's pushing up on the wire. And each time you cool it down, it goes back. So now the wire bond is seeing fatigue loading, and eventually the bond pad where it's bonded will fail. What makes it worse is this is not hermetic, meaning moisture is getting into it. Moisture is getting absorbed through all polymers absorb moisture, and that moisture eventually ends up accumulating and in those regions, and so the moisture causes corrosion on the bond pad. It cannot cause corrosion on the rest of the IC because it's covered with a passivation layer, silicon nitride passivation. But the bond pads are exposed so you can make electrical contact, and that's metal, and there'll be corrosion over there. So A, it's corroding over time. B, you're keeping on pushing on it over time. Collectively, it eventually causes a failure. So that's what that picture was. This picture is, well, actually it's a combination of more than that. So it corroded, kept fatiguing, and it partially lifted off from the bond pad. So this is the wire bond, this is the bond pad. And then what happens is as it partially lifts off, you have less and less area in contact, and you've got the same current going through smaller and smaller area. Eventually the current density is so high, you blow it off. You get an electrical overstress. So this is completely blown off, meaning melted because the current density got too high due to that complex interaction, corrosion, fatigue, and then electrical overstress. So it's a sequence of events that cause that failure. These are delaminations that have happened. This is a C-scan, acoustic C-scan of delaminations of, these are lead frames. So this package is a little bit different from that package. That package does not have a lead frame. This package is a little different. The die is on a central, and I'll show you pictures of all this later on, more details. The die sits on a metal frame. There are metal leads, metal fingers that come out on all sides, and now you can connect to the other end of those metal lead frames, and now you've got electrical connection into the die. So what happens is, again, because moisture gets in the package, and because the lead frame is metal, so that expands like a metal does. The coefficient of thermal expansion is roughly about, depending on if it's copper lead frame, about low 20s parts per million per degree C. But the plastic mold compound is much higher. Actually, these are special plastics that have been tailored for low CTE, but it's still higher than the metal. And repeated shrinkage and expansion will eventually delaminate that interface, and that's what you're seeing here. The red regions are in an acoustic scan. You're seeing the reflected signal showing you delaminations. So eventually, you get delaminations like that. Moisture then accumulates in those delaminated regions, accelerates the corrosion. So all of these are kind of, they feed on each other, they're chain events. Okay. So there's just 3 examples of the kinds of failures we see within packaged ICs. I'll go through a more exhaustive list this afternoon. Okay, and ICs, our active components, are not the only parts of electronics, as we said. That has passives, it has power supplies, for example, batteries. Batteries are notorious. Every cell phone that you guys own, assuming you don't abuse it, don't drop it or something, what do you think is going to die first? The battery. The electronics will outlive the battery. The display will outlive the battery. The battery is the first thing that's going to go. Why? That's because we just don't have the technology yet to make the battery as robust as it needs to be in those form factors that we're talking about, the form factors of cell phones and so on. This is actually, again, I'll zoom into that so you can see it. Sorry. So this is actually two different terminals in the battery. Well, not two different terminals, two different portions that have a potential gradient across them. And this is basically the insides of a lithium-ion battery. And this is dendritic growth. Metal has grown from one to the other in the form of dendrites. So these are dendritic growth. And this happens under the presence of bias and moisture. Okay, so if moisture gets into your battery, eventually this is of course an extreme case because we ran some highly accelerated tests in the lab. So in reality, you won't see such dramatic amounts of dendritic growth, but you'll see smaller dendrites that have grown from one cathode to anode through the separator sheet in between, and eventually those cause electrical shorts, and that causes a problem. So some of those fires that we were getting in lithium-ion batteries, Sony had the problem. Later on, Boeing had a problem. Boeing airplanes were grounded because of battery fires. Some of those were contaminants in the separator sheet that were accelerating the dendrite growth, or the shortages due to the dendrite growth. So dendrites are extremely important, and we'll talk more about that as we go through it. So building design models for dendrite growth is part of one of the many failure models that we design in physics of failure. So when you say, oh, I've designed a battery, I have to estimate its life. Before I build it, in the design stage, you'll use models for dendritic growth. So knowing all the materials and the dimensions, you'll be able to actually predict how much time in a given environment, how much time it takes to grow dendrites. Okay, and I'll show you examples of that later on. Okay, go back here. So that's work we're doing in batteries, and as you know, that's our biggest challenge. The reason we can't give you a better phone today is because we can't give you a more powerful battery. We can probably build you a much better phone, but it'll only last 2 hours between charges. That's of no use to you, right? So the battery is our biggest problem right now. It's the single biggest showstopper for portable electronics is batteries. And so building up the energy densities and the power densities of batteries is the holy grail. People are all looking for the next big technology. Lithium-ion is almost done already. People are moving to sodium-based batteries, which has been around for a long time. They're trying to miniaturize those for better applications. They're all before lithium-ion, we used to have the NiCad batteries, nickel cadmium, or the nickel metal hydride batteries. So those had didn't have quite as good a performance as we get out of lithium-ion. You can see where the lithium ions are. They're right out here, the tip of the outermost tip of the energy density and the power density curves. Okay. All right. And that's the problem, of course. If you make ones with extremely high energy density, you can't get a good power density out of it. And if you make ones with extremely high power density, you cannot get good energy densities out of it. The ideal is to stay on that diagonal line, and lithium-ion batteries get pretty close to that. Okay, then passives. So again, passives are a huge source of failures. If you talk to computer manufacturers like Dell, and you ask them, what is the single biggest problem you have with your computers over the last 20 years? Capacitor failures. It's a huge problem, okay? And that's part of it is because you saw how tiny capacitors are getting, okay? They are extremely small length scales, and now you have very little margin of error in the manufacturing process. Any defect during the manufacturing process at that length scale is catastrophic. So capacitor failures is a big problem, and mostly it's a quality issue. The design is okay, but when in order to cut costs, you go to cheaper and cheaper manufacturers, their processes are not as well controlled, and you get into capacitor problems. And of course, capacitors, there are many, many, many different kinds of capacitors. The pictures I had shown you earlier where I'm going to zoom into this image too. Sorry. So those are multi-layer ceramic capacitors. I'll show you more later on. There are lots of electrodes spaced closely apart, separated by dielectrics, and any short between them causes a problem. And why do you think shorts happen? Same reason in the battery, dendritic growth. So I'll show you work we do in predicting dendritic growth in ceramic capacitors. And as you get to higher and higher energy densities, we tend to move to other kinds of technologies, tantalum-based capacitors, aluminum-based supercapacitors. So some, and they come in various form factors. Some are of this kind of a rectangular form factor. Some are rolled, so the anode and the cathode are rolled up with separated sheets in them, and then you put it up in a can. You put it into cylindrical cans like that. You've all seen capacitors of this kind. So it comes in various form factors. And each one has its own. Some have liquid electrolytes in them, and then over time the electrolytes leak out, and that is what causes the degradation of the capacitor. So there are multiple degradation mechanisms, but the leading one is that dendrite growth. Okay. Also, we get a lot of micro cracks in capacitors. I'll show you zoom-ins of these later on this afternoon. Oh, by the way, that's an example of a dendrite in growing between two plates in one of these multi-layer capacitors. And like I said, there's a whole session dedicated to this in day 5. I'll talk about that then. And then the reason those grow is because these ceramic capacitors get micro cracks in them. Then moisture gets in through the micro cracks. That's how the moisture is available. And then the voltage gradient between the plates in presence of moisture creates those dendrites to grow. Okay, so bottom line, lots of physics of failure challenges in passives also. Okay, power supplies, passives. Let's go to the next one. So that was for components. So active components, passive components. Now let's talk about the interconnections and the circuit cards. So here are, again, I'll go through more details later on, but just an overview. Here are metal traces on a circuit card. You can see there's dendrite growth on the, so this is the surface of the circuit card, metal traces on a circuit card, and dendrites growing across them causing shorts. Again, in the presence of moisture, and of course you have lots of moisture, the circuit card is exposed to moisture. You see lots of moisture on the surface, and there are ionic contaminants from the processing of the printed circuit card. In the presence of all of that, you get rapid dendrite growth when you have a voltage gradient between neighboring traces. And it doesn't always happen just between neighboring traces. It can also happen between buried features, just not on the surface. Then we have holes drilled through the circuit card for connection through the thickness. You sometimes get dendrites growing from those plated, we call them vias, okay? V-I-A-S, vias, so sometimes they grow from the vias also. So dendrite growth, or the common term for that is ECM, electrochemical migration, okay? And the two kinds of electrochemical migration, one is dendrites, and one is what we call cathodic film formation. So this one grows from anode to cathode, this one grows from cathode to anode. Sorry, this one grows from anode, it's conductive anodic filament formation. This one grows from anode to cathode, this one grows from cathode to anode. This one happens, for this one to happen, this is, you're looking at a cross-section of a printed wiring board. This is the surface, this is a cross-section. These things that you're seeing are cross-sections of the glass fabric in the printed circuit card, and copper filaments form through them because the glass fiber debonds from the matrix. And this is just some testing we were doing to look at the debonding strength. So once it debonds, moisture gets in there, and then the copper migrates from one to another, one metallization to another. Okay, we also get other kinds of mechanical failures. This is fatigue failures in vias because of out-of-plane expansion. This is the cross-section of a printed circuit card. So the vertical direction is the thickness direction. The circuit card expands too much in the thickness direction. The copper cannot each time you heat it up, and then it shrinks down again, and that makes a cyclic loading in the copper, and eventually you get fatigue failures in the barrel, and that causes an electrical open. This is another kind of failure. This is a solder joint, a ball solder joint. It has a big void in it. Interestingly, the void didn't cause any problems. Okay, it survived the void fine, but if you look carefully enough, it has ripped out from the circuit card. Okay, so that happens a lot in high temperature solders. The printed circuit card cannot withstand that soldering temperature and initially gets damaged, and then that becomes a weak point, and then with repeated heating of the component and mechanical forces of the thermal expansion mismatch, eventually you crack that. That's called pad cratering. You can also see from back there, you probably cannot see it, I'll tell you, there's a crack through the metal trace here. So that you're looking at the top view of this crack over there, that crack has emerged through the metal trace, and now you have an electrical open. So these are all examples of different failure mechanisms or failure modes that we see in printed circuit card level and the interconnect level. And then if you go to the, and then the interconnect, the solder joint itself has a lot of failure issues. It's a very complex material. I'll spend a whole session on day 5 talking about that. So I don't want to spend time on it other than to point out, since Professor Ramanujam had pointed out, what do you do with composite materials? Even something that you think of, oh, that's pure metal, solder, right? Electronic solder that you do soldering with. That's a very complicated material. It's got all these intermetallic inclusions with tin dendrites. If you cross-section, it's a very complex microstructure. Then at the next higher length scale, it has multiple grains. And because tin is highly anisotropic, each grain has very different properties along its own principal crystal directions. So it's a very complicated structure. What seems to be like, oh, a nice homogeneous solder ball is anything but homogeneous. It is a highly heterogeneous structure with all kinds of internal stresses developing because of those internal heterogeneities, and that's why it failed. Okay, number one. Number two, he also talked about, Professor Ramanujam was very intuitive. He also talked about, what about the stress strain curves? These creep a lot. Like plastics, these highly viscoplastic materials. What does that mean? It means its melt temperature is very low. Plastics have low melt temperatures compared to metals. Solders are special kinds of metals. They have very low melt temperature. Why? Because we need to be able to solder it without damaging the electronics. So we choose metals with low melt temperature. The downside is, now even at operating temperatures, I'm very close to a melt temperature. What happens, those of you who are metallurgy based, or well, mechanical engineers who understand metals, what happens to a metal when you get close to its melt temperature? What happens to its mechanical properties? Sorry? Well, expand is the thermal expansion, but what happens to its stress strain behavior as it gets close to melt temperature? It reduces and okay, let's put it this way. I take a piece of copper, okay, and a copper rod, and I hang a weight from it. It's going to stretch a little bit depending on its modulus, elastic modulus, and assuming I've not exceeded the yield strength, it'll stretch a certain amount and stay there. If I leave that weight, it's just going to stay at that level forever for all practical purposes. Okay, I'm way below its yield strength, way below its ultimate strength, so it's not going to fail. It's just going to stretch a little bit because it has an elastic modulus, and it'll stop there. What happens if I take that same thing and do it at copper melts? Let's say this copper melts at about 1,000 degrees C. I do that same experiment at 900 degrees C. What do you think is going to happen? I hang it, it's going to stretch, and then I leave it. What do you think is going to happen? It's going to continue to stretch. Eventually it'll break, but it's going to continue to stretch all by itself, just under its own weight. Okay, I mean under the weight that I put on it. What do we call that kind of the first deformation was elastic deformation. What do we call this continuing deformation? No, plastic deformation would be, if I'd exceeded the yield strength, that would have been plastic deformation. This is creep deformation. Okay, so this is viscoplastic behavior. The word visco implies creep. So solder is, unfortunately, melt temperature of eutectic tin lead solder is 185 degrees C, close to 185 degrees C. And for lead-free solders, which is what we use mostly nowadays, it's close to about 215 degrees C. Okay? Even at room, and now think about that in Kelvin. How much is, someone do the math for me, how much is 215 in Kelvin is is about 488 Kelvin. Okay? So melt temperature is 488 Kelvin. Yeah, sorry, I'm left-handed, I'm sorry, so everything is crooked. Room temperature, which is 25 degrees C, in Kelvin is how much? 8, 9, 2, about 300, right? So what's the ratio? 300 divided by 488 is well above 0.5. Do you agree? Anytime you're above point, that's called homologous temperature. T sub H is shorthand for homologous temperature. Anytime you're above 0.5 homologous temperature, metals start to creep. In solder, even at room temperature, let alone at high operating temperatures, even at room temperature, you're way above the 0.5 critical threshold. So any stress in solder is going to cause a lot of creep deformation. So it's very hard to come up with a stress strain curve for a material like that because it depends on how fast I'm loading. If I load very slow, there's going to be not just elastic deformation but also creep deformation. So the stress strain curve at a low loading rate will be very flat because the deformation is both elastic and creep at a given stress. Whereas if I load very fast, it doesn't have time for creep, you'll see only the elastic part of the deformation. So if that is stress and that is strain, which one do you call it stress strain curve? Well, it depends on the temperature, it depends on the loading rate, it depends on a lot, and environmental conditions, depends on the grain microstructure, depends on a lot of things. So that's why Professor Ramanujan very correctly pointed out there are complex materials for which it's meaningless to just talk about one stress strain curve. It depends on the loading condition. Okay, so back to the solder. So the point is, there's if you look at the literature for solder failure and solder modeling and solder testing, and Anandaroop's already smiling at me, you can probably, if you do a Google hit, you can probably get almost 10,000 papers on it. There are people like me who have made their entire career studying only that material system and are still doing it. Why? Because tin lead solder is 5,000 years old. Lead-free solders are barely 20 years old. So we have relatively short body of knowledge in it, but very deep, because during those 5 years, hundreds and hundreds of scientists have looked at lead-free solders. But we're still not done. Do you know why? Because there's no one solder that industry has agreed upon. Every company sitting here has its own pet solder. And then they want to know what are its behaviors. What is its stress strain curve? What are its creep properties? What is its fatigue properties? How does it corrode? What are its thermal properties? What are its thermal expansion coefficients? And we're endlessly testing all of this to try to find out what those behaviors are. And some of these tests take long. Cyclic fatigue tests take weeks and weeks and weeks. Creep tests take days, okay? Because it creeps very slowly. I mean, I'm showing it like this, but in reality, you can barely see it. It creeps very slowly. I have to run the test for days and days and days, sometimes weeks and months at low stress levels to really understand creep behavior or quantify creep behavior. And why do we need that? Because those are the models that go into my design tools to find out how much deformation I'm going to get under field conditions. Okay? So wouldn't it be nice if instead of running those months and months of tests, I could actually predict, based on the microstructure, I could actually predict some of that behavior. So there's a lot of work being done on that kind of theoretical work, including in my group. I've got at least 3 PhD students who've done their dissertation just on that topic alone. These pictures came out of their PhD dissertations. That if they know the microstructure, they can actually predict what the creep curves will look like. Well, not that quite that simple. They need to know the properties of the individual constituents. That means they need to know the properties of pure tin. They need to know the properties of these intermetallic compounds. And then they need to know what this microstructure looks like. How large are the these particles? What are the average spacing? What are the average sizes of these? Those actually, we call those are the lobes of these dendrites. So what are the dendrite morphology? You give them that information, they can actually predict what the creep curves will look like with reasonable accuracy. So what that does is it saves them years and years of testing. So if you come up with a new solder, as long as it's got somewhat similar microstructure, we can actually cross-section it, look at the microstructure, and predict what the creep curves are. So that's the kind of research that goes on in these kinds of fields. Okay? So this is just to tell you the kind of work that's gone on. I'm not the only group in CALS that's doing work on lead-free solders. There are quite a few of us working on that. And over the years, we've worked in many, many, many different aspects of lead-free solders, all the way from whisker formation. That's, again, totally different. Anyone know about whisker formation? One or two, yeah. So what happens is, this is never-ending. Never-ending digressions, I apologize. So with whiskers, what happens is under mechanical stresses, long-term mechanical stresses, you start to see little single crystal whiskers growing out of the surface. So visually it looks like a fuzz ball. It's a ball with some fuzzy hair on it. If you look under a microscope, each of those hairs is basically a single crystal extrusion of tin. In this case, tin. For other metals, it'll be whiskers or whatever that base metal is. So whisker formation is a huge problem in electronics because these are slender whiskers, then they break off, then they migrate around, you're just floating around in electronics, they bridge across 2 metal traces, and you're done. Causes a short. So whisker formation is a massive failure risk. In fact, there are several NASA satellites that NASA claims in outer space, so there's no way to confirm, but they believe those died due to whisker formation. Expensive satellite missions died because of whisker formation. So a lot of resources are spent studying whisker risk mitigation and how to deal with that. So one is they cause shorts. The other is if I've got 2 of these solder joints with whiskers growing towards each other, when they reach a certain proximity, they'll start to arc, and that causes problems. Okay. All right. Anyway, so as I said, over a long period of time, I told you people have studied this a lot, and this is just in our group. I'm not even talking about the other hundreds of scientists who have been looking at it all over the world, not just in the US, Europe, Asia, everywhere. You open any journal in China, in Japan, in Korea, in the US, in Europe, and even here, I know scientists from India who've been studying solders a lot. So it's a complex material system, or families of material systems, and a lot of work going on in that. So including things like what is the vibration fatigue durability, what is the temperature cycling durability, what are these microstructural properties, corrosion, visco formation, studying all of these. So CALS itself has produced textbooks, book chapters, hundreds of papers, and so on. Okay. All right, so that is all the interconnects at level 2. Remember the hierarchy: level 0, level 1, level 2, level 3. Now let's go up all the way to level 3. In level 3, we have all these connectors and connecting wires, wiring harnesses, connectors. That also is a problem. So one of the leading causes of failures we see in electronic boxes, let's say your desktop computer. One of the big problems, there are several. I mentioned capacitors, that's a key problem. But the other big problem we find is it's not working okay, you unplug it, replug it, works fine. Again, after a few months, not working okay, unplug it, replug it, works fine. It's a connector that's causing problems. So the connector basically corrodes, okay? And this is not corrosion you can see. These are micro corrosion, spots of corrosion, and the base metal comes out through those corrosion pores, and now you've got shorts, okay? So now you're getting electrical shorts. But if you remove it once, it wipes everything clean, and reinsert it, it works again for a few weeks until the next short happens. So you get both. Sometimes you get shorts because the base metal has come out and shorted, and sometimes you get opens because the corrosion products have built up a hillock, and now the two contactor surfaces are no longer making contact. So you get both. Either way, when you remove it and put it back in, it cleans out all that debris and it works again. So connectors usually have a wear metal surface on top, typically something soft like gold, okay? The gold is A, preventing from corrosion, but B, you need a soft contact. You cannot have hard contact surface in connectors. Does that make sense to you? If you have two hard surfaces, what's the problem? Surfaces that look smooth to you with the naked eye, I'm going to write again. So two contactor surfaces that are making contact like this, in reality, if you zoom in, is one surface like this and another surface like that. If these are hard surfaces, then they're making just point contacts. On the other hand, if these are soft materials, and remember all connectors have some spring force in them. So under the spring force, these will start to, all those contact points will start to yield. Okay, so if there's a soft metal, the contact surfaces will start to yield. So these points now become contact surfaces because of localized yielding. So that's why we need a soft metal on the surface. The second thing is gold is not just soft, it's also noble metal. Prevents from corrosion. So it protects the base metal from corrosion. So that's why high reliability connectors have these soft gold coatings on them. But the problem with soft materials is what? It also wears out. Each time you're plugging and unplugging it, it's wearing out the gold. Don't even have to unplug it. If there's vibration loading, like an automotive, just the micromotion from vibration is going to wear out the gold. The thermal expansion mismatches due to heating and cooling causes micromotion that will wear out the gold. So the wear resistance is also a key issue. And the wear resistance is not just the metal, it's also interface between the base metal and the surface metal. So we do a lot of tests on wearability, wear characteristics of the coatings. So this is just a little tool that we use for that kind of fretting corrosion. Fretting corrosion means multiple things. It means wear due to fretting. You understand the word fretting? Fretting is relative motion, and wear due to relative motion. That's fretting. So fretting wear is the full term. And then because of that fretting wear, the surface metal is gone, base metal is exposed, that corrodes. So fretting corrosion is a combination of fretting wear and corrosion. And then you get creep forces that relax the spring forces, that causes problems and so on. So again, this is an example of kinds of problems we run into at level 3 interconnections. And then there are, other kinds of interconnections. So polymers. Polymers is a big problem for us. Electronics is full of polymers. There's a lot of information there. Let me start with some of these. This is basically an IC chip on the top. This is the substrate on the bottom. And the interconnection, instead of solder balls, we have a conductive adhesive. A conductive adhesive is nothing but a polymer filled with conductive spheres, little particles, micron scale particles. So these are micron scale particles. And the idea is here you're making electrical contact. So you have the substrate, you put down the polymer adhesive, the conductive adhesive, which is filled with these conductor particles. You put the chip down and you just glue it together. Then you cure it, it just glues together. And now these conductive particles in between, instead of solder joints, are giving you the electrical connectivity. Of course, the conductive particles here too, but there's nothing to connect to, so it's fine. The problem is if you get enough conductive particles going laterally, now you have a short between neighboring pads, and then you have a problem again. So you have to carefully control what's the density of particles you have given the pitch size you have between your neighboring pads. Okay, so that's one kind of polymer. And again, there's a lot of work we do on those kinds of polymers. Reliability of those polymers is a big problem. They delaminate, moisture gets into them and changes their properties. There are all kinds of issues that happen. They slowly lose compression force, because you need compression force to have the right contact resistance. You lose that compression force, the contact resistance becomes too high. So all of those are degradation mechanisms in conductive adhesives. Again, there are bodies of researchers, including my group, that do a lot of work on that. Other kinds of adhesives that are not electrical, that are just performing a mechanical function. The display is mounted in the magnesium case here, not with any metal fasteners, just glued in, literally just glued in. Your cell phone battery case is just glued in, and they're glued in with what we call pressure sensitive adhesives, PSAs, pressure sensitive adhesives. That means you press it hard enough, they just glue it. It's as simple as that. They cut gaskets of the right shape, place the gasket, press in the display, done. End of manufacture. How reliable is that? Well, it's a big problem. So failures of PSAs, these are laminated glue sheets. So this is just these PSAs come in multiple layers. It's a fairly complex system. And they're capable of very large deformations. Again, unfortunately, there won't be time to talk about this particular case study. So maybe I'll just zoom in now and tell you a little bit about it, because we won't be talking about this anymore in this course. But again, there's a PhD student in my group who's working in this area. So you can see this whole joint, this is an aluminum piece. This is just a test specimen. 2 aluminum pieces that were bonded together with PSA, and they were this close to each other. The thickness was just about that much. It stretched about 1,000 times its initial length, the initial thickness. That's how much deformation they're capable of, but at a cost. What it does is forms these big cavities inside and fibrils. So what was originally just homogeneous becomes these isolated cylindrical fibrils with lots of cavities in between. That's how it deforms. Okay, and they're capable of a tremendous amount of creep deformation. So displays eventually warp because of creep deformation of these PSAs, and that's why you start to see light leaking around the edges of those displays. That's because the PSA has warped. And then this particular one is what we call a double layer PSA. You can see there was a separator sheet in between. There's one layer below it, one layer above it. In this particular test, they're both delaminated. And if you were to cross-section that and look at it from the top, you would see all those cavities. These are the cavities, these bubble-like things. These are 4 different images, by the way. Before loading, no cavities. As you continue to load, more cavities, more cavities, more cavities, and eventually it fails. So each of these each of these cells is a cavity, and the web around it is the long fibrils. It's the cross-sectional view from the top. Okay? And you can see they're capable of very large deformation. These are stress-strain curves. Again, going back to Dr. Ramanujam's question, stress-strain curves, look at how complex these are. Stress goes up, stress comes down, stress goes up, stress comes down, eventually goes up, and it fails. Very complex systems. So understanding these, again, I need quantitative models. It's not enough to give me a pretty picture. I need to design so this is going to live 3 years for whatever life cycle load is. A pretty picture doesn't solve it. I need a model for it. So how do you model these deformation phenomena? That's what people are working on. Okay, so one of my PhD students is working on these. So he can actually predict, if you tell him what the initial material system is, what's the separator sheet, what's the material system, what are the dimensions, he can actually predict what those stress strain curves will look like. Okay, moving on. So to add to the complex set of fun stuff we're talking about is now printed electronics. We no longer make electronics just the old subtractive way. Now we directly print everything we want. In the old days, as you saw, you'd make a silicon IC on a wafer, you would package it, you would put wires, solders, printed circuit board. Now we don't do all that. We print everything in place, right down to the semiconductor. So the substrate, the interconnects, the semiconductors, everything is being printed one after another. The dielectrics, the conductors, everything is being printed in place. Okay? There's no more individual pieces that you join. No more joining. Everything in one sitting is a full, complete, functional electronic system. Okay? That's how 3D electronics are being made in some cases. I'm not saying all electronics are built that way, but one big class of electronics is being built that way. So printed electronics has become a big thing. There, the material systems are entirely different. The microstructures are entirely different because the fabrication process, now a printing process, has porosities, all kinds of different kinds of defects. So the failure mechanisms there are huge, new ball of wax, new set of problems. We're not going to have the time to talk about it in this workshop, unfortunately, but I just wanted to put that on your radar. That it's another big area of research. Again, those of you who eventually end up in research, some of the students will end up in research. 3D printed electronics is a hot area to get into. Okay? This picture is interesting for a totally different reason. I'm going to zoom into that. So this is a study actually that we're doing collaboratively. I'm not a printing expert. I work with other printing experts. My interest is what are the new failure mechanisms in printed electronics. So my collaborator in that is a colleague called Professor Siddharth Das, who's well known to Anandaroop. He's a PhD of this institute. He's now a colleague of mine at University of Maryland. We work together. He's a fluids mechanician by training. Now he does a lot of other stuff. But he's the one who's modeling. But these are traces that were made by inkjet printing, not inkjet, aerosol jet printing. So you aerosolize the ink, and then you throw it out with along pre-planned tool path. You throw it out at the substrate, and that's what forms these metallization patterns. So all these metallization patterns were done with inkjet printing on a substrate. So, not inkjet, aerosol jet printing. And there are a lot of problems with it, issues with it. So Dr. Siddharth Das's group does a lot of computational modeling to try to optimize those printing processes. So all of this is actually out of models that his postdoctoral scientists are building right now as we speak. They're working on that part of it, and I'm working on what are the failure mechanisms for those electronics. Okay? All right. These were all, by the way, built by 3D printing. Remember, I talked about solder balls. Well, these are to replace solder balls. So you make polymer balls, and then you coat the polymer. Instead of having a full metal solder ball, you have a polymer ball, and you coat metal on top of that polymer. Now you have a conducting ball. So instead of a solder ball, you have this. So these polymer bumps are made by printing, and then the metal is printed on top of that. The point is, making these complex, high-profile shapes is not at all easy in printing. Printing is good for 2D, two-dimensional printing. Printing three-dimensional shapes is a challenge. So that's why it's in the research domain, is people are learning how to print this. This too was done by Professor Das's student. Okay, so both of these are being printed by Professor Das's students. Okay. And we go on and on. I'm not going to have to end this session because of time constraints. But the point is that same thing with power electronics. Power electronics are a beast all their own. You have power diodes. You have high power field effect transistors. You have IGBTs, which are bipolar junction transistors. So you have different kinds of high power. So there the current densities and the voltage gradients are huge compared to conventional microelectronics. So these have posed special challenges. Power electronics pose special challenges because of the extremely high current densities, extreme high heat, and extremely high voltage gradients. So there are a certain set of failure mechanisms that dominate in power electronics. And that's important in every class of electronics you're talking about. Power electronics, all the way starting from the power supply for my laptop, right? The power supply that you plug into the wall and has a little box in it, to power supplies for LEDs, to automotives. The power supplies for automotive electronics is pretty high, needs pretty high rating, all the way to industrial electronics, aircraft and space electronics. The power supply modules on those are extremely challenging to design and to make them robust and reliable. Okay, so my colleague, Professor Pat McCluskey, works exclusively in this area. Okay, so I keep talking about all these failure pictures of failure modes here, some substrate cracks and so on. So I keep talking about these failure modes. Well, this is a list of all the different failure mechanisms that are, and I'll talk quite a bit about this over the next 5 days. This is just the first glance you're getting. This will be our table of contents for the next 5 days. Okay, we're not going to cover everything on it. There's just not enough time. We teach semester-long courses that cover only half of it. Okay, so but this is a list of all the dominant important failure mechanisms that we have run into, or people who build electronics run into over the lifetime of electronics. And let me just show you how it's a kind of a table of contents, and then we won't spend any more time on it. So that it's organized in two different ways. First, look at the color organization. On the right-hand side are what I earlier called wear-out, cumulative degradation wear-out mechanisms. On the left-hand side are the sudden catastrophic overstress mechanisms. And then as you go down vertically, I've separated the failure mechanisms out into those that are caused predominantly by mechanical stresses, those that are caused predominantly by temperature, those that are caused predominantly by either electrical current or voltage gradients, then those that are caused by high energy particles, typically in outer space, or even doesn't even have to be outer space. Any exposed electronics on base towers, cell towers out in the field is actually constantly getting dosage of cosmic high energy particle radiation, and they have to survive that. And then other kinds of harsh chemicals. So let's take just one set of examples to give you a feel for how the information is organized. So on the mechanical side, what happens if you put a sudden large mechanical stress? You may exceed the yield strength, right? The material may plastically deform, like your connector over here, right? If I force the connector that's partially bent, what will happen? It'll completely bend the connector pin. That's plastic deformation because of excessive force. So that's yielding. For mechanical engineers, that's common term we use, yielding, when you get past the yield strength. Or it may fracture if it's a brittle material, like what happened to this guy. It dropped on the hard floor and you exceeded the fracture toughness of glass and the glass shattered, right? So that is brittle fracture, so that's fracture. Or interfaces may debond. So it may not be here, the failure was in the glass. The other example I gave, the failure was in the deformation in the copper of the pin, connector pin. But now the failure may be at the interface. So I talked about PSAs, pressure sensitive adhesives. Those sometimes will come apart. If you drop this, you may not fail the display, but the display may debond from the frame. And that's because the adhesive interfaces fail. So sometimes the failure is interfacial. So the failures may be inside a material or at the interface of two different materials. Same example, mechanical stress on the wear outside is cyclic fatigue. If I take a paper clip, bend it back and forth enough number of times, what happens? It snaps into two. All mechanical engineers understand that that's cyclic fatigue, right? So then creep. We already talked about creep. So that's again a time dependent. If the product sees mechanical loading for a long period of time, eventually it'll creep, right? So if the temperature is high enough and the stress is high enough. Then wear. I talked about connectors with micromotion fretting wear. So these are all examples of degradation we see in electronics due to mechanical stresses. Similarly, temperature causes its own problems, and we'll be going through several of these in detail next 5 days, so I don't want to spend more time on it, so other than to just explain how the information is organized. Now a few subtleties. One, there's usually interactions which, just to keep this chart simple, I didn't show those interactions. For example, temperature, not just mechanical stress, but temperature also accelerates creep. Remember I talked about copper getting up to 900 degrees C before the creep becomes substantial. So temperature also accelerates creep, but I didn't put the creep over here. I still put it under mechanical, because if I start putting all these dotted lines, there'll be lines everywhere. The chart becomes unreadable. So just for simplicity, I didn't show some of those interconnections. But the reality is that multiple stresses can together jointly trigger a given failure mechanism, and vice versa. Mechanical stress can cause multiple failure mechanisms. Electrical stresses can cause multiple failure mechanisms, and so on. Same thing, by the way, with these electromigration. It's not just current density, it's even temperature. So there should be a dotted line from temperature to electromigration. I've eliminated all the dotted lines for simplicity. Okay, so that's the second subtlety here. The third is the red side and the blue side are interlinked. Meaning, if I fatigue, so let's say this glass has fatigued a lot over time because of, or not fatigued, corroded over time. Glass does corrode, by the way, okay? Glass corrodes in harsh environments. Not something we think about very automatically. We think, oh, glass, that doesn't corrode, metal corrodes. Glass corrodes, which means its properties degrade over time if it's exposed to a harsh environment. So a glass that's brand new today, my cell phone is brand new today, it may be able to survive a 1 meter drop onto concrete. But 2 years from now, after it's seen all the environmental corrosion, it may not be able to survive that same drop because its properties have degraded, which means the wear out, corrosion, is now interacting with the overstress fracture. So there's interactions between the red side and the blue side. And vice versa. I may drop my cell phone and cause a residual stress because of plastic deformation, cause a residual stress in a connector, and now that connector may no longer last for 3 more years, it may only last 2 more years. That means it now fatigues faster because of that residual stress. So that overstressed fall has reduced the fatigue life. So interactions. One more thing, one final thing. So every time I put a name of a failure mechanism here, in our world of physics of failure, so physics of failure is dealing with these failure mechanisms. So that's it. This is the entire workshop, physics of failure workshop, and all the entire career, my career and all the other people who claim, oh, we are physics of failure people, is all included in that one chart. There's nothing that we do that is not in that chart. Okay? All we do is what's on that chart. But what does that mean? What does it mean to say I do what's on that chart? It means I do research on what exactly goes on in the material under mechanical stress. What is fatigue? Why is it failing? How do I make it more robust? Which materials are more fatigue resistant? Where's a mathematical model for that fatigue degradation? Because the designers need a model. They need to be able to predict how many years this product will survive. It's not enough to say, oh, this one is more fatigue resistant than that one. Well, how much? This one lasts 2 years. Is yours going to last 3 years, 5 years, 10 years? I need to put a number on it, which means I need a quantitative model. I need quantitative model constants, which are material properties that I can measure in the lab. So I need to be able to build those kinds of models, do the kinds of testing to get the model constants, and put that all in catalogs. And they're there for standard materials like steel and all. You just open steel handbook, all the fatigue constants are there for different steels, aluminum alloys, copper alloys. They're all cataloged. We need to be able to do the same thing for metals, materials used in electronic systems. But the biggest challenge, like I said before, is the length scale. We're not dealing with steel bridges. We're not dealing with steel girders or aluminum beams. We're dealing with micron scale, nanoscale structures that are fatiguing, that are off the length scale of their individual microstructural heterogeneities. It's an order of magnitude more difficult problem than the old days of, oh, let's just go into the lab, measure some fatigue, and put the properties in out. Now the fatigue properties are a function of the environment, they're a function of the prior history, they're a function of the microstructure, which means it's a function of how you processed it. It is a multidimensional problem now, okay? Which is, another word for it is called job security. I've been doing this business for 30 years. I can probably, if I live long enough, I can do it for another 30. Okay, all right. So that's what I meant by when you say physics of failure, it means you are researching quantitative information about each of these failure mechanisms to the extent where designers can now use these information to design against any of these failure mechanisms. Okay? And I wouldn't say design against, it's really designing for, meaning you're designing the system to survive these environments for as long as your customer needs it to. I don't want to design something that resists fatigue for 100 years. That's a waste of money. That costs me money. I want it to last exactly, if I'm giving you a 3-year warranty, I want it to fail on 3-year day 1. Then I don't owe you any money, and you're going to buy a new product on 3-year day 1, right? That's the level of control we need on the product. That takes research, okay? And especially at these length scales, okay? Okay, 3-year day 2, I'm losing money. I want to be making money. The customer is making the money. I want to make the money, okay? All right. Okay, so I've been over these slides, skip over all this. Accelerated testing, I'll talk a lot about this later on. Accelerated testing is something that's important, okay? I talked about the fact that if you are trying to learn about the robustness of the product through accelerated testing after you've built some prototypes, it's too late. So what you really need to do is when you're designing it, you need to have very high confidence based on these models, quantitative models I'm talking about. You need to have very high confidence that you have designed a product for year 3, day 1, okay? But then at the end of it, you need to still confirm, because there's always a surprise, okay? We are engineers, we know that there's always surprises. So you need to run some accelerator tests to convince yourself that, okay, I did the right job in the design and there are no surprises. What does that mean? You're going to test for 3 years and 1 day? By then your competitor has stolen the market, they're in generation 2 product and you're still testing in the lab, right? So what do? That's what we call accelerated stress testing. You increase the stress levels so that you fail the product not in 3 years, but perhaps in 3 days or 3 weeks at most. Sometimes maybe a month at most. A month is already too much. Your business manager is going to say, are you crazy? Don't you know your job? Can't you do this faster? So you need to accelerate these failure mechanisms, those blue and red failure mechanisms. You need to accelerate them in a controlled way so that you can cause failures. That same failure that would have happened in 3 years in day 1, you want it to now happen on 3rd day and hour 1 by accelerating the stress levels. The question is, how much do you accelerate the stress level? Well, that depends on how good your model is. Your model should tell you what percentage should I increase the stress level to shrink the life from 3 years to 3 days. Okay? And obviously that depends on which failure mechanism you're targeting and how good your models are. Do we know that absolutely well today? No, we are far from perfect. We have some good ideas. Sometimes we do a good job. For some of those models, we are further along than others. And for some of them, we still don't do very well. That's why we need you guys. There's boatloads of research still to be done. Okay? And not just that, the technology is rapidly changing. By the time you guys are in the workforce, all the materials I spend my lifetime testing are all going to be gone. You're going to face a new set of materials, new set of processes, new length scales. You're back to square one, which means the research can never stop. Okay? Okay, so the point is we do testing, accelerated testing to verify our design, but design is not the only problem. Remember I talked about it. You might have the best design in the world, but a lousy manufacturing engineer can kill your product by doing a poor manufacturing. So you need to know how the product's going to behave not just as designed, but also as manufactured. So designing the right fine-tuning the right manufacturing process is a very important step. So there's accelerated testing done there too to verify that you have fine-tuned your manufacturing process correctly. And then even after you're done with all that, batch to batch, there could be issues. You've got a good design, you've got a robust process, but the slang we use for that is someone lost their recipe, right? You came up with a good cooking recipe, but someone lost their recipe and they changed one of the masalas and now it doesn't taste right anymore. So that's what quality assurance testing is for. Every batch, you retest a little bit, some small subset, some sample, just to make sure that batch came out right and that someone didn't mess up something in that batch. Some machine on the assembly line didn't go out of control on that particular run and you didn't end up with a quality issue. So quality assurance testing is also the people do accelerated stress tests to see if those everything survives the way it's supposed to or not, and so on. So those 3 boxes, well actually 4. I'll talk about that one later on. And these are, by the way, common terms in industry. You guys probably already recognize them. EV testing, that's engineering verification testing. There you're proving a given technology. Okay, then DV testing, you're proving your design. And PV testing, you're proving or verifying your process. So 3 kinds of testing that is extensively done. And then routinely you do quality assurance testing once you're in manufacturing cycle. This bathtub curve, I'm going to come back to it much later. Let's skip that one. Okay. Okay. So here are some examples of accelerated testing we do in the lab. So I talked about capacitors growing filaments. We grow those routinely in accelerated manner. We have models that can predict how they'll accelerate. So that solid line you're seeing is our model. So our model can predict what's going to happen. But again, at the length scales we're talking about, there's a lot of piece-to-piece variability. That's just intrinsic to the defects in the material because you're down at the length scale of the defects in the material, in the microstructure. So this kind of variability is very, very common. So the best that the model can do is give you a mean value, and then you have to have some distribution around that prediction based on the variabilities introduced by your materials and your manufacturing. And these are just pictures of dendrites that are growing inside ceramic capacitors. Same thing with fatigue, solder fatigue, copper fatigue. We do a lot of fatigue, thermal cycling fatigue testing, okay, power and thermal cycling fatigue testing. We do a lot of combined temperature cycling and vibration. So this is a vibration shaker. It shakes the circuit card deforms that way. I mean, exaggerated in a computer model, of course, but it basically vibrates. That's the first mode of vibration. Yes, those of you who are mechanical engineers and have done vibration understand the first mode, second mode of vibration, right? So this circuit card was clamped along these 2 vertical edges, and then those are the 2 edges, and then shaken out of plane and you can see it's shaking out of plane and deforming in this computer model. And then we do that vibration at different temperatures. So we set different temperatures in the chamber. The shaker head is inside, the specimen is inside, and it shakes it at different frequencies, different PSD profiles, different amplitudes, different frequencies, and we generate failures, and we build vibration fatigue models out of those. Then here's another very unique shaker that we have in my lab. This is a 6-axis shaker. This is a single-axis shaker. This is a 6-axis shaker. This is the table that's That's the table. So the specimen, in our case a circuit card, is usually mounted there. And then you can see 4 actuators on x-axis, 4 actuators on y-axis, and underneath, you cannot see it, there are 4 actuators in the z-axis, the vertical out of plane. And by firing these in the right sequence, you can produce vibration in x direction or y direction or z direction or combinations of those. Or you can do rotations. For example, if take the x pair, if I were to fire these two 180 degrees out of phase with those two, I would rotate that table. So you can also do rotation. So we can do full 6 degree of freedom. 6 meaning 3 translation, 3 rotation. 6 degree of freedom vibration on these shakers. So that's a pretty sophisticated shaker. I mean, they're not that commonly available in industry. Then we do a lot of drop testing. We talked all day today about dropping products. Well, we need to be able to test those. So we have drop towers. We do a lot of drop testing. In fact, some of the MEMS microphones I showed earlier, we have tested those for some niche applications for some sponsors up to about 30,000 Gs. So this tower, in principle, goes up to 100,000 Gs. We have taken it only up to about 30,000 Gs, which is very high. If you think about the JEDEC standards for electronics, they ask you to test about 2,500 to 3,000 Gs. We're talking about an order of magnitude higher over here. But this is for a very specialized application. But the point is that most testing labs have these kinds of very sophisticated capabilities for specialty applications of electronics. Okay, I'm going to skip over this one because this is on, I talked about prognostics and health management. That means you can actually have an age meter that tells you what fraction of the life has been consumed. I don't do a lot of work in this area. I do only a specific thing. We call them canaries. I design canaries for health monitoring. The concept is very simple. Have you heard the phrase canary in a coal mine? No. In the old days in coal mines, I don't know if they did it here, but at least in the US they used to do that, and even in Europe. They used to put these canary birds, C-A-N-A-R-Y, canary birds, right? Canary birds in the mines because there would be toxic fumes in mines. And the idea was if the bird died, then you knew there was excessive fumes, all the humans would exit immediately. So it was kind of a warning sensor. It was a sensor. But intentionally weaker than human. Toxicity level that kills a canary is much smaller than the toxicity level that takes to kill a human. So if the canary dies, you know you still have enough time, you have to exit. So it's an intentionally weakened specimen, so it fails before the functional, in this case functional people or the human people fail. So canaries in electronics are the same thing. We intentionally design weak subsystems or weak elements in our electronics so that they will fail under the same life cycle stresses. They will fail before the functional parts of the electronics fail. So that way you have early warning, okay, and you design a canary for 50% life, 80% life. The canary fails, you know you've used up 80% of the life of the product. So my job is to use physics of failure principles to intentionally design weakened structures to act as canaries. But rest of it is very sophisticated, a lot of data analytics and so on, a lot of computer scientists working in this with our teams. I'm not going to get into that, okay? Okay, so that's all PHM. Here are some of the data analytics tool sets. So the software tools that we use all these machine learning data analytic algorithms. It's beyond my body of knowledge, okay? Beyond my pay grade, as I say, okay? And then I talked about supply chain management already. So there's information that has to go up the supply chain for proper physics of failure-based reliability assessment. And there's information that has to come down the chain. That means if you're telling this guy this has to survive, so I'm here, okay? And I'm telling this guy, you better sell me a component that survives in my product. Well, what's the first question this guy's going to ask? What is your environment, right? If you don't tell me what your environment is, I can't give you a robust product, right? So there's information that has to flow down. The operational stresses, the environmental stresses. Not only that, he's going to want to know, well, what other manufacturing steps are you going to put it through? Because the biggest source of stress in the life of a product is the manufacturing. The manufacturing is extremely harsh as far as stresses go, okay? So you need to know what are all the manufacturing steps here, because that is going to cause damage to the product, and then ultimately the end user, is going to cause more damage to the product. So all of that information goes up and down. So if you talk to someone like Dell or Microsoft, they have extensive communication lines through standard specs and everything with their supply chain to convey that kind of information. So I myself did a sabbatical at Microsoft for a year. They've got sensors in every crate that's shipping these around the ocean from China to Japan to Hawaii to Singapore to US and Europe. They've got sensors on every ship, every handling depot, every transportation step, and of course in every factory, measuring what are all the stresses the product is going through before it gets to the end user. And then they've got sensors inside that's telling them what the end user is doing. So everything I do on this, better believe it, Microsoft knows by the end of the day, not a human being there, but their computers know by the end of the day what I've done to this machine. It's constantly talking to the cloud. Okay? So that's how all these computers are built. You may think you have privacy, you don't. They're watching your computer all the time. They're not taking any, they'd be sued if they were taking your data from it, but they're taking your machine performance information out of it. It's all in the fine print that you signed when you bought the computer. Okay. So there, as I mentioned, there's a lot of work in reliability that has to be done in supply chain management. And finally, cost optimization. You have to trade off warranty cost versus how much cost does it take to make a more reliable product, and you look for the optimum price points where the warranty cost just balances out the reliability cost. My slang for that is that's the 3-year day one cost. Okay. That's it. Let's stop over there. I've already explained what's the cradle-to-cradle cost optimization. This slide I'm not going to go over. I did want to briefly give a shout out to the CALT Center again. Everything I'll talk about of the rest of the days will be out of work I've done at CALTS and learned out of CALTS colleagues. So if you want more information on those, you have to go on the CALTS website with a big caveat. You'll be able to get the titles and the abstracts, but a lot of times those are just papers. So then you go to the journal and get the paper there. You won't be able to download it from our website because it's password protected for sponsors. Our sponsors require us to do that. But you can just get the citation out of here, go to the journal or the conference proceeding and download it there. I would say there's a wealth of information over there, and not just on our website. Every center like ours has websites like that. I would say those are great resources for you guys to when you need information. Okay. How are we doing in terms of time? Should I start the next module? Okay. So the way the contents are arranged, the next one is, so the next 2 slides are an area you know a lot more than I do. Okay. It's not about packaging. It's to get to packaging, I need to talk briefly about what you're packaging. What are you packaging? Semiconductors and passives and other stuff, but at least semiconductors.